GCE Advanced Level Chemistry Practical Series Experiment number 43 Preparation of Biodiesel. The aims of this practical is to prepare an environmentally friendly liquid fuel source and to understand the advantages of biodiesel. Now let's take a look at our introduction here. Biodiesel is produced from non-volatile plant oils. Plant oils contain triglycerides. Biodiesel is a mixture of several methyl esters of fatty acids. Now students, during the past couple of years, we have actually had a renewed interest in this particular fuel source, which is biodiesel, and you may have observed that there was a lot of conversations revolving around biodiesel. So in today's experiment, we are going to be taking a look at how we can prepare biodiesel. Now to begin with, biodiesel is a mixture of methyl esters of fatty acids. So there are sometimes in a given biodiesel mixture, there can be different types of methyl esters of fatty acids. So it's a mixture of methyl esters of fatty acids. And students, we can prepare biodiesel with the use of non-volatile plant oils. If you carry out a process which is known as trans-esterification, then at that point, the product that you obtain, one of the products that you obtain, is known as biodiesel. So, without further ado, let's look into how this process is done. Before moving on to that, let's identify what plant oils contain. Now, plant oils contain these types of triglycerides. So, this is an example of a triglyceride. And these triglycerides are the ones that we use in the process of manufacturing biodiesel. So each of these bonds that you see over here, is an ester bond. You can break these ester bonds and carry out a process known as trans-esterification, which will result in the formation of glycerol and our methyl esters of fatty acids. Now, fatty acid methyl esters collectively in this process that are getting produced is known as biodiesel, and the other product would be glycerol. Let's take a look at the text that is given here. Below are a few plant oils that can be used for the production of biodiesel: palm oil, soybean oil, sunflower oil. These are some of the oils that we can use for the production of biodiesel. Other reagents that are needed for the production of biodiesel are listed here. You can actually take vegetable oil, sodium hydroxide, and methanol. So apart from these plant oils or vegetable oils, we would need sodium hydroxide and methanol. Sodium hydroxide and methanol are the other two main reagents you would need for this process. Producing biodiesel by reacting plant oils with methanol and sodium hydroxide. The plant oil undergoes reaction with methanol facilitated by sodium hydroxide acting as a catalyst. So students, when you're trying to produce biodiesel, you have to choose first of all a plant oil. It has to be a non-volatile plant oil, right? So, and that plant oil has to contain triglycerides, right? Some plant oils contains free fatty acids, and when it comes to producing biodiesel, the free fatty acid content in a plant oil should be very low, right? We have to have a plant oil that contains a lot of triglycerides, and we are going to react these plant oils that contain triglycerides with sodium hydroxide and methanol. Now over here, sodium hydroxide acts as a catalyst. Sodium hydroxide acts as a catalyst. And in the trans-esterification process, now you will learn in detail what trans-esterification is, but for the time being, students, what happens here is the triglyceride contains ester bonds. As I mentioned earlier, you can see these triglycerides, they contain ester bonds. So each of these bonds that we have over here are ester bonds. These are all ester bonds, right? So these ester bonds, students, bear with me a second. These ester bonds can be broken with sodium hydroxide, and as they break, they react with the methanol that is added, and a trans-esterification process takes place. During this process, the triglyceride present in plant oil, or more precisely, the esters in the triglyceride undergo a transformation into methyl esters. Now students, you can see here, this is a triglyceride, and each of these bonds are an ester bond. These are all ester bonds. So basically a triglyceride is an ester. So when we are trying to produce biodiesel, what we do is we convert one ester into a different type of ester. Actually, what we do is we remove the alkyl group that is connected to this ester and we convert it into a methyl ester, right? So that is what we are doing in this experiment. This chemical conversion is termed trans-esterification. The resulting product, known as a biodiesel, is the mixture of methyl esters derived from this reaction. Now students, you can see that in this particular triglyceride, there are three C double bonded OR groups, right? There are three of them. And you can see three ester bonds as well. We break each of these ester bonds with the use of sodium hydroxide, and when we are adding methanol, these alkyl groups that are present over here are going to be replaced with methanol groups. So what you finally produce is a methyl ester. You can see here, as you can see, a methyl group is now present here. So what we have formed here is a methyl ester, and the other product that is getting formed in this reaction is glycerol, also known as glycerine. Biodiesel is a mixture of methyl esters. Biodiesel is a mixture of methyl esters. So it's not a single type of methyl ester that you get. So it's a mixture of methyl esters. In a triglyceride, there can be different types of fatty acid chains present in a single triglyceride. So when we carry out this trans-esterification process, you will get a few different types of fatty acid methyl esters. So we have a mixture of methyl esters produced at the end of this process, and that mixture of methyl esters is what we know as biodiesel. The plant oil that is used to produce biodiesel is also an ester. However, it is not a methyl ester. Keep that in mind. The plant oil that we use is also an ester. All of these are ester bonds, as I mentioned earlier. So triglyceride is consisting of three ester bonds. However, the triglyceride is not a methyl ester. In the process of producing biodiesel, one ester is turned into another type of ester. One ester or triglyceride has ester bonds, so it's a specific type of an ester. Then when we add sodium hydroxide and methanol, this specific type of an ester turns into fatty acid methyl esters or methyl esters of the fatty acids present in the triglyceride. So therefore, students, what you do over here is conversion of one type of ester into a different type of ester. So we say this process is a trans-esterification process. Trans-esterification process. One type of an ester is converted into a different type of an ester. This process is known as a trans-esterification process. As the main byproduct of this process, glycerin, also referred to as glycerol, will be formed. And we can very clearly see the reaction that is taking place. You can see that the methanol that is added is going to react with the carbon that is indicated here, and this ester bond that we have over here will be broken. The ester bond that we have over here will be broken, and you will eventually form this glycerol, and over here into each of these fatty acid part of the triglyceride, a new CH3O group will be attached, turning them into fatty acid methyl esters. In short, we also call them FAME, fatty acid methyl esters. So the mixture of these fatty acid methyl esters is what we call biodiesel. So here we can see fatty acid methyl esters are formed. So you can see the CH3 group that we have now introduced through this process. So what we have formed is a mixture of fatty acid methyl esters, and a mixture of this is also known as biodiesel. This is a nucleophilic substitution reaction. You can see this CH3O group is now substituting this section of the ester, and this particular reaction was initiated by an attack from the lone pair present on this oxygen. So this is acting as a nucleophile, and as this nucleophilic attack takes place, you can see one part of the molecule gets replaced by another section. So this is a substitution. So this is known as a nucleophilic substitution reaction. One thing that we have to mention here, sodium hydroxide here is acting as a catalyst. So sodium hydroxide is used as a catalyst here, and we employ higher temperatures like 50 to 60 degrees Celsius temperatures to make sure that this reaction happens more efficiently. Industrial biodiesel production process. Step 1. Treating the plant oil taken as the raw material. So free fatty acids and non-saponifiable compounds in plant oils are removed. So students, these free fatty acids in plant oil actually can interfere, not only those, even non-saponifiable compounds in the plant oils can interfere with this trans-esterification process. Now we will see how they can interfere in a while. So we have to first remove these free fatty acid content in a plant oil source. This enables to have a high yield by the trans-esterification reaction and maintain a high level of purity of biodiesel obtained. So we need a high level of purity, students. Otherwise, now we use biodiesel. After manufacturing biodiesel, we use them in many applications, and one of them is going to be the use of biodiesel as a liquid fuel in motor vehicles. So at that point, if you have a lot of impurities, it could damage the engine as well as other components in a vehicle. So we do not want these other impurities in the fuel source here. So we have to make sure before we start this process to remove other unwanted impurities from the plant oil, especially free fatty acids and non-solidifiable components. Now, free fatty acids can actually interfere with the trans-esterification process as well. We will learn about it in the next part here. If plant oils contain free fatty acids of the type RCOOH, they might react with sodium hydroxide to give soap. Now, you know soap is basically sodium salts of fatty acid, or sometimes potassium salts of fatty acids. So students, if you have free fatty acids in our oil mixture or in the vegetable oil that you take, when you add sodium hydroxide as a catalyst, a saponification reaction can take place, right? So soap can be formed in the biodiesel mixture. If soap is formed, foam is also generated, which inhibits the catalytic action. So this is the reason why we don't want free fatty acids in the oil. Actually, when we are selecting an oil, we try our best to select an oil with very low free fatty acid content in the oil. Now, plant oils contain both free fatty acids as well as triglycerides, and we have to choose a plant oil with really high triglyceride content and very minimal free fatty acid content, so that we can easily remove the free fatty acid content and then move on to producing biodiesel. Thus, in plant oils, for use of this particular purpose, the free fatty acid content should be less than 2% weight wise, and the acid value should be 0.1 milligrams KOH per gram. 0.1 milligrams KOH per gram. So weight wise, the free fatty acid content should be very low. Now, as I've explained before, when the free fatty acid content is high, there will be a lot of soap produced, which also can produce foam in the biodiesel mixture. And apart from that, the catalysis that is done by sodium hydroxide will be hindered due to the formation of soap. Step 2. Preparation of catalyst mixture. Sodium hydroxide catalyst is dissolved in methanol. Afterwards, the solution is mixed with triglyceride, in this case the plant oil that we have chosen. It is very important that the alcohol does not contain water. Now, in this process, we do not want to introduce water into the process. Otherwise, we can produce other products other than biodiesel. So in order to avoid producing any other products, we have to make sure that the alcohol that we use, in this case methanol, does not contain any water. In addition to sodium hydroxide, compounds such as potassium hydroxide, sodium methoxide are used as homogeneous catalysts. Now, students, what are homogeneous catalysts? Catalysts that are in the same phase as the reactants are known as homogeneous catalysts. You should remember this. So, any catalysts that are in the same phase as your reactants are known as homogeneous catalysts. So, potassium hydroxide and sodium methoxide can be used as homogeneous catalysts. We are using liquids here, and we can obtain potassium hydroxide and sodium methoxide as liquids as well. Compounds like magnesium oxide and zinc oxide can be used as heterogeneous catalysts. So magnesium oxide solid, zinc oxide solid can be used for this catalysis process, and at that point, since they are not in the same phase as the reactants that are used, they are referred to as heterogeneous catalysts. I hope you remember these two words. By now, of course, you should know these things. So homogeneous and heterogeneous catalysts, their differences are very clearly explained. Homogeneous catalyst means whenever you use a catalyst, if the catalyst is in the same phase as the reactants, then it's a homogeneous catalyst. If the catalyst is in a different phase compared to the reactants, it is a heterogeneous catalyst. Step 3. Reacting triglycerides with methanol. Reacting triglycerides with methanol. Since the alcohol and plant oil are immiscible, they are mixed with continuous stirring while the temperature is maintained between 50 to 60 degrees Celsius. So students, these triglycerides or the plant oil and the alcohol will not mix really well. They do not mix really well. So therefore, in order to make sure that there is enough contact between the two reactants, we have to continuously stir the mixture. So at that point, we can ensure that these reactant particles are coming into contact with one another sufficiently to produce the final products that we want to obtain. The trans-esterification reaction occurring here produces biodiesel and glycerol. Now students, as I mentioned earlier, to ensure that this reaction has enough activation energy and happens in a bit of a higher rate, we have elevated the temperature to 50 degrees to 60 degrees Celsius temperature. So at these temperatures, we can ensure that the reaction will happen at a sufficient rate. And after this reaction has happened, we call this reaction a trans-esterification reaction. And after the trans-esterification reaction has happened, we will form methyl esters, right? You can see this section is a methyl group now. So this is a methyl ester. So a mixture of methyl esters is referred to as biodiesel. Mixture of fatty acid methyl esters are referred to as biodiesel. So what you produce here is biodiesel, and this product here is glycerine, or we can also refer to it as glycerol. Right, so we have biodiesel and glycerol produced. So we come to step 4 here, separating the products. The main products exist as two phases because they do not mix. So the fatty acid methyl ester is not soluble with glycerol, or glycerol is not soluble in fatty acid methyl ester. These two layers are not miscible. So there will be two layers formed. The upper layer consists of biodiesel, unreacted triglycerides, and diglycerides. So we have unreacted triglycerides, diglycerides. Only one part of the triglyceride has reacted at that point. So we have triglycerides and then we have diglycerides, and we can have biodiesel in the upper part of these two layers. So when the reaction is carried out, we can transfer the reaction mixture into a separatory setup, right? So industrially you will observe there will be two layers produced, right? If you are doing this in the lab, you can transfer the mixture into a separatory funnel. So you will see on the top layer you have your biodiesel along with triglycerides and diglycerides, and at the bottom we will have your glycerol. And glycerol and methanol in small amounts will be present in the upper layer as well. A small amount of glycerol and small amount of methanol can also be dissolved. The lower layer contains mainly glycerol with excess methanol and the catalyst. So lower layer mainly contains glycerol along with some methanol and excess catalyst, and the upper layer mainly contains biodiesel along with diglycerides and triglycerides and a very little amount of glycerol and methanol. After the separation of the phases, these layers are separately taken into different containers and we can obtain biodiesel that way. So after the layers have completely separated, sometimes when you carry out a reaction like this, for the layers to separate out in the reaction mixture, it will take some time. After the layers have very clearly gotten separated, then you can separate out the two layers and obtain the biodiesel layer that way and the glycerol layer separately. Step 5. Further purification of crude biodiesel. Now we know the biodiesel have some impurities. What are the impurities that are there, students? We have triglycerides, diglycerides, certain amount of glycerol, and methanol also is there. When biodiesel phase is washed with water, glycerol, methanol, and the catalyst dissolved in it can be removed. So if you have any water-soluble impurities in the biodiesel, when you wash the biodiesel with water, these water-soluble impurities will be removed. Finally, it is possible to remove water. So after we washed the biodiesel with water, we can finally remove water. Remaining methanol may occur in both layers of biodiesel and glycerol as an impurity. By separating and heating the layers, the methanol contained in them can be removed. This methanol can be reused. So students, now after separating the two layers, we know there are certain methanol impurities present in both the layers. And methanol is volatile. It can easily be evaporated. So if you heat glycerol as well as your biodiesel, you will be able to evaporate the methanol that is present in the two layers. So this evaporated methanol can be collected and reused. Water is bubbled through biodiesel to purify it by removing sodium hydroxide and glycerol, which are present in it as impurities, and then water or the moisture sticking to the biodiesel is also removed. So students, as I mentioned earlier, we have other impurities in the biodiesel, right? Like glycerol, we have sodium hydroxide that was used as a catalyst. Small amounts of them can still be present in the biodiesel layer. So as mentioned in the initial paragraph, we are going to remove them by washing the biodiesel with water, and then later on water also can be removed. As mentioned in the initial part of this slide, you can see we are using water to remove other impurities that are actually soluble in water. For example, sodium hydroxide, glycerol, these impurities that are present in biodiesel layer can be removed by washing the biodiesel with water. We say we can bubble water through biodiesel. So students, after removing the impurities that are soluble in water by washing biodiesel with water, now there can be small amount of water in biodiesel because we use water to wash biodiesel, right? So we can have a small amount of water now in the biodiesel layer. So to remove water also, we can heat the biodiesel and evaporate the water. If needed, even vacuum conditions can be used when trying to remove water that is present in the biodiesel layer. So, as mentioned here, water is bubbled through biodiesel to purify it by removing sodium hydroxide and glycerol, which are present in it as impurities. Then, water or moisture sticking to the biodiesel is removed mainly by heating. Now, students, we looked at how biodiesel is prepared in an industrial setup. So, let's now take a look at how we can produce biodiesel in the lab. So, when you are preparing biodiesel in the lab, there are some precautions you need to take. So, let's take a look at that. Students must wear eye protection while performing this experiment. So, one of the precautionary measures you should keep in mind when conducting this experiment is to wear eye protection. Equipment and chemicals required. So, these are the equipment and the chemicals that we'll be using in this experiment. We'll be using Erlenmeyer flask, beakers, separatory funnels, and chemicals would be vegetable oil, sodium hydroxide, and methanol. So, let's take a look at the procedure. Add 0.5 grams of sodium hydroxide into a 250 milliliter Erlenmeyer flask with methanol and stir vigorously until all of the sodium hydroxide is completely dissolved. So, did we use water here? No, we are using methanol to dissolve the sodium hydroxide. So, in this case, we are using sodium hydroxide and methanol, actually 0.5 grams of sodium hydroxide, and we are adding methanol to it, and we are dissolving all of the sodium hydroxide first. Warm up 100 cubic centimeters of unused vegetable oil to about 40 degrees Celsius in a 250 cubic centimeter beaker. Used vegetable oil must be filtered and water removed before using it for biodiesel production process. So, students, that is also another very important detail. You can use used vegetable oil for the production of biodiesel. However, you have to remove any solid impurities that are present in used vegetable oil, as well as any water that is present in used vegetable oil. Then only you will be able to use it for biodiesel production. If not, in the lab when you are conducting this experiment, it is always recommended to take unused vegetable oil. So, we have to heat it up to about 40 degrees Celsius, and then introduce the vegetable oil sample into sodium hydroxide and methanol mixture while stirring. Continue stirring for about 20 minutes. Until two layers appear, and then allow the mixture to settle. So, students, we have to keep stirring. The mixture for about 20 minutes or until two layers appear. As we know, when you keep on mixing it, you will notice that the reaction begins to take place, and glycerol and biodiesel will be produced, and these two layers will separate. And at that point, you can be sure the reaction has taken place to a sufficient extent. So, after you can very clearly see the two layers getting formed, we can stop stirring the mixture and we can allow the reaction mixture to settle. Transfer the contents to separatory funnel. Allow the layers to separate for another 30 to 20 minutes, and then remove the top layer. The bottom layer is glycerol and the top layer is methyl ester, or in other words, biodiesel. So, students, when it comes to separating this mixture, we carried out this reaction in a beaker, 250 milliliter beaker, right? So, we have our vegetable oil, we added our sodium hydroxide and a methanol mixture, and then we started stirring continuously, because as you know, even the sodium hydroxide methanol layer will not mix very well with vegetable oil. So we have to continuously stir it to ensure that the reaction happens properly. And as we continuously stir it for about 20 minutes, then you will see two layers start to separate, and even one layer will turn a little brownish yellow in color. So at this point, where you see two layers very clearly, we can be sure that the reaction has properly taken place and we have produced biodiesel and glycerol. And we will allow the mixture to settle for a while, and then we will transfer it to our separatory funnel. So as you transfer it, there will be a small amount of mixing taking place. So we will allow another 20 to 30 minutes for the two layers to properly separate again. And then the top layer and the bottom layer will be separated out. Now, top layer contains biodiesel along with some impurities, and the bottom layer will contain glycerol along with impurities like methanol and sodium hydroxide. Soak half of a paper strip in the separated top layer, burn it, and observe the rate of combustion. You can soak a filter paper and then burn it to observe if it is the paper that is burning or if it is a fuel that is burning, right? So this can be observed after the whole process is completed to observe whether you have properly prepared your biodiesel. So now we can move on to the next slide. So these are the observations when you're carrying out your reaction. So we can add our methanol and sodium hydroxide mixture into our vegetable oil. Of course, vegetable oil, based on what type of vegetable oil you use, will have a yellowish color to it, right? Some vegetable oils have a very prominent yellowish color, some will have a slight yellowish color. However, it is going to appear yellowish in color. And we will heat it and we'll stir it for about 20 minutes. And when you do that, you can observe the formation of a yellowish brown color mixture. And if you allow it to separate out, you will see two layers. So this is an indication that the reaction has started to happen. So in this slide, we are going to take a look at biodiesel, a small introduction again about biodiesel. So biodiesel is a sustainable alternative to the petroleum fuels that are currently in use, and biodiesel is a renewable fuel. So students, this statement is very true. So we know the petroleum fuels that we are currently using are not renewable. So these crude oil sources can be exhausted when you continuously consume them. So we have to now turn to renewable energy sources. So we do look into solar energy, wind energy, or harvesting energy from other sources. And one of the options that we currently have, apart from these types of energy sources, is another type of renewable energy, which is biodiesel. Biodiesel is a renewable liquid fuel source, and compared to petroleum fuels, biodiesel is a sustainable fuel. Petroleum fuel is a non-renewable source of energy. Burning of petroleum fuels releases carbon that originated from fossils, converting it into carbon dioxide. So students, this is very important, that when it comes to petroleum fuels, they release carbon into the atmosphere in the form of carbon dioxide that was originated in fossil fuels. This process contributes to an increase in the amount of carbon dioxide in the atmosphere, leading to severe environmental problems such as global warming. Consequently, our attention is being directed towards the production of energy using renewable sources as a sustainable alternative. Now students, when it comes to talking about a renewable energy source, we have to keep in mind a renewable energy source is an energy source that can be replenished within a considerably shorter time frame. Now, when you're talking about fossil fuels cannot be replenished after you use it in a considerably small time frame. In order to form fossil fuels, it will take millions of years. So, we cannot consider fossil fuels as a renewable energy source. As you know, renewable energy sources are energy sources that can be replenished within a very short period of time, or within a considerably short period of time. However, fossil fuels is taking millions of years to get formed. So if you take fossil fuels out of the ground and then you use it, the carbon that is trapped in fossil fuels is now released into the atmosphere as carbon dioxide, and this carbon dioxide, to get fixated in plants, it will take some time, and then these plants to again turn into fossil fuels, it will take millions of years. So students, the carbon cycle is not a closed looped carbon cycle. What we do is we take the fossil fuels out of the ground and then we burn it and release carbon dioxide into the atmosphere. So there's an overall increase of carbon dioxide in the atmosphere, right? There's no carbon fixation going on and producing fossil fuels again within a short, narrow time frame. Actually, to fix carbon dioxide as carbon in plants and then turn them into fossil fuels again, it'll take a considerably long time period. So we can't consider it to be a renewable energy source, right? So it takes millions of years to produce fossil fuels, but it takes just few years to use it. So therefore, students, we can't say that this is a closed-looped carbon cycle. What we do is we actually produce more and more carbon dioxide and release it into the atmosphere when we use fossil fuels. So this has very detrimental outcomes, right? We know when the carbon dioxide levels in the atmosphere goes up, one of the most detrimental outcomes we can think of is global warming, right? We'll take a look at the ramifications of global warming in a second. So this type of an issue is not going to be associated with the use of biodiesel, because when it comes to biodiesel, we use plant materials, we use plant oil, and imagine we use plants in the manufacturing process of biodiesel. However, let's say we take a plant, we use it to produce biodiesel, and biodiesel releases carbon dioxide into the atmosphere, and that carbon dioxide can be again fixed by our plants, and those plants can again be used for the production of biodiesel. So the carbon dioxide that is released into the atmosphere with the use of biodiesel actually came from a plant, and this carbon dioxide that is released into the atmosphere can again, within a considerably short period of time, can be stored back in a plant, which can again be used in the process of producing biodiesel. So this is more or less of a closed carbon cycle, where you would not additionally introduce any carbon dioxide into the atmosphere. So this can be considered a renewable energy source. Now we are looking at the increase of carbon dioxide levels in the atmosphere due to burning of fossil fuels. Fossil fuels such as coal, crude oil, and natural gas are formed from remains of ancient plants and marine organisms that accumulated and were buried over millions of years. And these organic material undergo heat and pressure, transforming them into fossil fuels. So students, when you talk about biodiesel, to grow a plant, to use it and again grow another plant, it doesn't take that long, right? We know we grow a plant, you use it for biodiesel manufacturing. Now carbon that was in the plant is now in the biodiesel. We burn the biodiesel, carbon dioxide is released into the atmosphere, and those carbon dioxide can be stored back in a plant due to carbon dioxide fixation. and then we can use that plant again for biodiesel manufacturing. So students, you can see, to grow a plant, it wouldn't take a very long time, like millions of years, right? Within a span of 10-20 years, sometimes even less than that, we can have the carbon dioxide that is released into the atmosphere through biodiesel be fixated in a plant again. So this is a renewable energy source. But can we say the same about fossil fuels? No, it takes millions of years to produce these fossil fuels, right? So that is what we are talking about here. When we burn these fossil fuels for energy, carbon that was stored in them is released into the atmosphere as carbon dioxide. This combustion process is a major contributor to increase in carbon dioxide levels in the atmosphere, contributing to the greenhouse gas effect and climate change. When we have high levels of carbon dioxide in the atmosphere, it contributes to the greenhouse gas effect and it warms up the atmosphere, which will lead to global warming. The fixation rate of carbon dioxide through the formation of fossil fuels is an extremely slow geological process that takes millions of years. So you can see this particular process, geological process, takes millions of years to form fossil fuels. So when you take fossil fuels from the ground and when you use it and release carbon dioxide into the atmosphere, to fix that amount of carbon dioxide again in fossil fuels, it takes millions of years. So it's not a relatively smaller time frame, right? So therefore, the fossil fuels are not a renewable energy source. The organic materials such as plants and marine organisms accumulated and undergo heat and pressure over extended periods, transforming them into fossil fuels, as mentioned earlier on. So this geological process does not happen in a very short period of time. It happens in a very large period of time, like millions of years. So therefore, students, we can't consider fossil fuels to be a renewable energy source. The fossil fuels that you use today, the carbon that is released into the atmosphere through the fossil fuels that you use today, will not be fixed back in fossil fuels in a short period of time. It will take millions of years. In contrast, combustion of fossil fuels for energy is a rapid process that releases stored carbon back into the atmosphere as carbon dioxide. So we are now knowing very well that this is not a renewable energy source. We take fossil fuels and release the carbon that was stored in fossil fuels back into the atmosphere. The rate at which we burn fossil fuels far exceeds the natural geological process that create them. So the rate at which we release the carbons into the atmosphere is extremely high related to the process that this carbon is stored back in fossil fuels. Because storing the carbon back in fossil fuel takes millions of years, but releasing them into the atmosphere through the burning of fossil fuels takes very short period of time. As a result, the release of carbon dioxide into the atmosphere outpaces the slow rate at which carbon is fixed into fossil fuels, contributing to the significant increase in atmospheric carbon dioxide levels, which is key driver of climate change. So we are aware of this now. As we continuously use fossil fuels, we are now releasing a lot of carbon into the atmosphere in the form of carbon dioxide, and we only have a very slow rate of converting carbon dioxide in the atmosphere into fixed carbon in plants or in fossil fuels. So therefore, students, due to the differences in the rates, we have carbon dioxide levels increasing in the atmosphere, which is going to contribute to climate change. Environmental impacts due to increase in atmospheric carbon dioxide levels. So one of the most significant environmental impacts is global warming. And then we have listed down some repercussions that are associated with global warming. Rising temperatures. Global warming leads to an overall increase in average temperatures worldwide. Now, we are currently experiencing this increased temperatures as well. So, as we have higher carbon dioxide levels in the atmosphere, which contributes to global warming, one of the very first things we are going to notice is overall elevated temperatures worldwide. Melting ice and glaciers. Higher temperatures cause ice caps and glaciers and polar ice to melt, contributing to rising sea levels. So, as these ice caps are in the two poles, they will melt, the sea levels will rise. So, the rising sea levels could be problematic, especially to small islands, because they are at risk of completely being submerged. Third point, sea level rise. Melting ice and thermal expansion of seawater contribute to an increase in sea levels, threatening coastal areas and low-lying islands to be completely submerged. Right? So, apart from the melting of ice caps, due to the increase of temperature, seawater can thermally expand, increasing the sea levels. So, therefore, students, the coastal areas and low-lying islands are going to be at risk, because as the sea levels rise, certain parts of the coastal areas or some islands can be submerged. Extreme weather events. Global warming is associated with an increase in the frequency and intensity of extreme weather events such as hurricanes, heat waves, droughts, and heavy rainfall. So, students, you might have observed some of these extreme weather events over the news in the past couple of years in all over the world. So, students, you can see due to global warming, the frequency and the intensity of these extreme weather events have increased. So, this is another outcome of global warming that is caused due to high carbon dioxide levels in the atmosphere. Ocean acidification. The absorption of excess carbon dioxide by the oceans lead to increased acidity, negatively impacting marine ecosystems and species like coral reefs. So, this can impact the aquatic life that is seen in different oceans, especially when the sea water is becoming more and more acidic. It can impact the marine life that we see in the ocean. Disruption of ecosystems, shifts in temperature and precipitation patterns disrupt ecosystems, affecting biodiversity, migration patterns, and availability of resources. So, students, this affects the entire ecosystem. As you know, some birds or different animals, they have their migration patterns, right? So, based on the changes that are happening in the climate, they might not be able to any longer carry out these migration patterns that can affect their existence. Let's take a look at the 7th point. Threats to agriculture. Changes in climate change can affect crop yields, posing risk to food security due to altered growing conditions. So, as we increase the temperature in the atmosphere and due to global warming, due to these altered conditions that we have explained in the previous steps, now we have crops growing under different conditions. So, this could lead to food scarcity and increased pests, and even water scarcity can be a problem. Loss of biodiversity. Global warming accelerates the habitat loss and changes, contributing to the decline and extinction of many plant and animal species. Now, we saw earlier in a previous step, ecosystems will be disrupted. This could lead to the extinction of certain plant life as well as some animal species. Health risks. Increased temperature can lead to more heat related illnesses, the spread of vector borne diseases, and challenges to mental health due to extreme weather events. Now, we think extreme weather events can only physically hurt us, but that is not always the case. They can also bring about mental health related issues as well. The 10th point is economic impacts. So we can see in the 10th point they are talking about the various adverse effects of global warming, which can result in significant economic costs, including damage to infrastructure, increased healthcare expenses. So, of course, when there is an extreme weather event, when there are damages to infrastructure, and apart from that, it could also create many health related expenses in the population in that area and challenges to agricultural productivity. So, these things will have a significant economic impact. Social displacement, rising sea levels, and extreme weather events can lead to displacement of communities, creating climate refugees. So, even social displacement can be another problem. Resource scarcity. Changes in climate patterns can lead to water scarcity, which will affect drinking water supplies and agricultural irrigation. So, it will not only affect drinking water or having enough water for human consumption, it will also affect agricultural practices as well. So, students, these are some of the impacts that we can expect through global warming due to the increase carbon dioxide levels in the atmosphere. So, carbon dioxide levels in the atmosphere will be increased with the continual use of fossil fuels. So now in this slide we are going to be looking at why won't the carbon dioxide levels in the atmosphere increase significantly when using renewable fuels. When using renewable fuels, why won't the carbon dioxide levels increase in the atmosphere? So renewable fuels such as biodiesels don't contribute significantly to an increase in carbon dioxide levels in air. We knew this, right? So let's take a look at the explanation here. This is because they are derived from recently captured carbon dioxide during the growth of plants or other renewable sources used in their production. So, in the biodiesel, the carbon that is there is carbon that was very recently fixed into plant materials, right? These carbon was not removed from the atmosphere millions of years ago. So, we are not taking carbon that was fixed from the atmosphere millions of years ago and then releasing it back into the atmosphere. We are not doing that when you are burning biodiesel. Now, biodiesel uses plants and plants that are living actually to produce plant oils, and then after that plant oils are used to produce biodiesel. So, the carbon that is found in biodiesel came from recently fixed carbon dioxide, right? Recently in the sense within a short period of time, not millions of years ago, maybe about 10, 20 years time frame. Then these fuels are burned, they release carbon dioxide, but this is offset by the carbon dioxide previously absorbed by renewable feedstock, meaning plants that we use. Essentially, it is a closed carbon loop, making renewable fuels more susceptible choice with minimal impact on atmospheric carbon dioxide levels compared to traditional fossil fuels. So students, when you burn biodiesel, the carbon dioxide released is going to be stored in plants, and this storing or this fixation of carbon dioxide can happen fairly within a short period of time. And these plants can again be used for the production of biodiesel. So this is a closed loop carbon cycle. So there will not be an increase of carbon dioxide levels in the atmosphere. So we can see this closed loop carbon cycle here. We can see biodiesel is burned and atmospheric carbon dioxide is produced, and atmospheric carbon dioxide is fixated in plants, and these plant oils are extracted. Again, plant oils are turned into biodiesel with the use of methanol. Now sometimes the use of methanol could be making this renewable fuel not a type of renewable fuel, but we can also produce methanol with the use of biomass. So at that point, students, this entire process can be carried out with the use of only plant material. So this becomes a renewable fuel source due to that. The balanced chemical equation of the reaction that produces biodiesel will be looked at now. So you can see here we have a triglyceride, right? In this case, the R groups are considered to be the same. In this example, you can see the same fatty acid is present here connected to this glycerol molecule, forming a triglyceride. So you can see when this triglyceride is reacted in the presence of sodium hydroxide and methanol, the methanol group will attach to this ester, forming a methyl ester. So you can see we will form methyl esters. We can call this fatty acid methyl esters. FAME is the abbreviated form. So a mixture of fatty acid methyl esters are also known as biodiesel. And apart from the main product biodiesel, we also get glycerol. Another small detail here. Instead of R indicates the alkyl group, the hydrocarbon chain. There can be R1, R2, or R3, which means each of these fatty acids or hydrocarbon chains can be different to one another. There's no rule saying they have to be the same. At this point, the reaction should be balanced accordingly. You can see the balance equation here. So if they have a R1, R2, and R3, basically three different hydrocarbon chains connected to each of these fatty acid parts of the triglyceride, you can see the esters that are formed are written accordingly, because we will form three different methyl esters. Each of these are different methyl esters. They are not the same because we have R groups changing here, R1, R2, and R3. So these are a mixture now of fatty acid methyl esters, which is also known as biodiesel, and glycerol will be formed as another product. So in this case, we can see here R1 is C17H35, and then we have R2 C17H33, and the last one is, students, C15 C15H31. So I will explain why I changed that in a second. I want you to see, when you talk about these fatty acid parts or hydrocarbon parts of the fatty acid chain, through the formula of it, we can identify whether the fatty acid hydrocarbon chain is a saturated hydrocarbon chain or an unsaturated hydrocarbon chain. Now students, if you get a terminal carbon that is seen in a hydrocarbon section of an organic compound, the terminal carbon always have 3 hydrogens, and the carbons that are found in the middle of the hydrocarbon chain, if there are only carbon-carbon single bonds, you will usually have 4 bonds, and 2 of them would be carbon-hydrogen bonds. You can see each carbon contains 2 hydrogens. Only the terminal carbon contains 3 hydrogens. So you can see if I add another carbon, you can see again only 2 hydrogens are there. So normally in a fatty acid there will be the carboxylic acid group. So I have drawn the carboxylic acid here. So you can see when you write this section, we can write this as C double bond O, OH, and this is going to be the R group. This whole section is going to be referred to as the R group. Now let's write the formula of the R group. Right? How many carbons are there? 1, 2, 3, 4, 5. In this particular example that I used, there are 5 carbons. So we write C5. And how many hydrogens are there? Except for the terminal carbon, students, all the other carbons only have 2 hydrogens each. Now the terminal carbon has 1 additional hydrogen. So there are 5 carbon atoms in the hydrocarbon part of this acid. So 1, 2, 3, 4, 5 carbons are there. So since each carbon has 2 hydrogens, we can multiply 5 by 2, which is going to be 10. And we have to add 1 additional hydrogen because the terminal carbon always has 1 additional hydrogen compared to the other carbons. So therefore, students, the formula of this hydrocarbon part of this acid is going to be C5H11. C5H11. You can see 1, 2, 3, 4, 5 carbons. Each carbon has 2 hydrogens. So 2 into 5 is 10. 10 plus this additional hydrogen makes it 11. So C5H11, and then the acid group will be there. So over here as well, when we have these formulas, we can actually figure out whether this is a saturated hydrocarbon part of the fatty acid or not. Right, so R1, when we write R1, COOH, actually I can write the ester that is formed. This is the fatty acid methyl ester we had formed. So the R1 part, the formula that they have given for R1 was C17H35. H35. And then this part. So C17H35 means, students, if there are 17 carbon atoms, only the terminal carbon atom can have 1 additional hydrogen. So all the other carbons will have only 2. So for the time being, we'll consider all the carbons to have only 2 hydrogens. So then 17 multiplied by 2 is going to be 34. We shouldn't forget the additional hydrogen in the terminal carbon. So then when we add that, it's going to be 35. So is this carbon chain a saturated hydrocarbon part? Is this section a saturated hydrocarbon chain? The answer would be yes, this is saturated. Because we do not see any double bonds. Because in the presence of double bonds, the number of hydrogen atoms will be less, right? So we attributed 2 hydrogen atoms to each carbon. That's why we wrote C17 multiplied by, if there are 17 carbons, each carbon, if it has 2 hydrogens, then what happens? 2 hydrogens per each carbon mean when you have 17 carbons, altogether 34 hydrogen should be there. There's 1 additional hydrogen here. What is that hydrogen? Hydrogen attached to the terminal carbon. Terminal carbon has 3 hydrogens, whereas the middle carbons usually have only 2 hydrogens. So then again, there was another one, which is C15, the one that I changed, C15H31. right? Even in this case, students, if you take the methyl ester that was formed, the final product. So even in this case, there are 15 carbons, right? Each carbon has 2 hydrogens. That means there should be 30 hydrogens and one additional hydrogen seen in the terminal carbon. Each carbon has 2, but the last carbon has additional 1, so we add that. So altogether 31. Altogether 31. So if you go back, you can directly write 31. Is this saturated? Is this part saturated? Yes. Again, this part is saturated. We saw that each carbon had 2 hydrogens when producing this formula. We also saw C17H33. C17H33. We'll write the methyl ester of that part. Fatty acid methyl ester. So over here, if each carbon is to have 2 hydrogens, then what happens, students? If each carbon is to have 2 hydrogens, then the hydrogen number should be 17 multiplied by 2. We know the terminal carbon has 1 additional hydrogen, so we have to add that. 17 multiplied by 2 is 34. 34 1 plus 1 is 35. So we should have 35 here, but the hydrogen number is 33. So how many hydrogens are missing here? How many hydrogens are missing? We are missing 2 hydrogen atoms. Why would that be? You might notice whenever there is a double bond in a hydrocarbon chain, you will observe, now imagine we have this saturated section of the hydrocarbon, right? So if I ask you to write the formula of this saturated section, right? If I ask you to write the formula of the saturated part of the hydrocarbon, you will write, there are altogether 4 carbons here. Each carbon has 2 except for the last carbon here, terminal carbon here. Everything has 2, so therefore it's 8 hydrogens there, and the last one has 1 additional one, so therefore 8 plus 1, 9, C9, C4H9, right? So this is representing a saturated hydrocarbon section. However, if we we'll remove 2 hydrogens here, so that we can include a double bond here, because each carbon can form only 4 bonds. So did you notice, in order for me to add a double bond, I had to erase 2 carbon hydrogen bonds, or in other words, I had to remove 2 hydrogens from the saturated hydrocarbon chain. So what happened at that point? So the formula is going to show 2 carbons, or 2 hydrogens, not 2 carbons, 2 hydrogens less. Do you understand? So when you have a double bond present in the carbon chain, it is going to take away 2 hydrogen atoms from the formula. So if you have 2 double bonds, at that point you can expect the absence of 2 or 4 hydrogen atoms. If there are 2 double bonds in the hydrocarbon section, it will result in the removal of 4 hydrogen atoms. So I hope that is clear to you. So over here we can see that the saturated hydrocarbon section that I drew earlier had a formula C4H9, and the unsaturated hydrocarbon chain that I have drawn here has a formula C4H7, right? So this is a clear indication that there are 2 hydrogens missing, which represents the presence of a double bond, or which represents the unsaturation seen in the hydrocarbon chain. So therefore, in this particular compound, you can see we are missing 2 hydrogen atoms, meaning this hydrocarbon chain that you see here in the carboxylic acid part of this ester is going to be unsaturated. This is unsaturated. Right, students. So with that, we can move on to the next part. If excess concentrated sodium hydroxide is added, a saponification reaction can happen and soap can be formed as one of the products. So the soap formulas are given here. So instead of having the right amount of methanol and the sodium hydroxide catalyst, if you increase the sodium hydroxide catalyst, if you had excess amount of sodium hydroxide, at that point you are going to have, instead of this methyl esters forming, you will have soap forming. A saponification reaction can happen. So this will interfere with the formation of our biodiesel. We don't want soap to be produced while we are producing biodiesel. So you have to use the right amount of sodium hydroxide. Now in this slide, we look at the importance of the use of biodiesel. Biodiesel is free of sulfur, unlike petroleum fuels. Consequently, burning biodiesel does not generate sulfur dioxide. So one of the problems with petroleum fuel is the use of presence of sulfur, and when you burn petroleum fuels, sulfur dioxide can be released into the atmosphere, which can lead to acid rains. This absence of sulfur dioxide emissions during biodiesel combustion means there is no contribution to environmental pollution typically associated with sulfur dioxide emissions. So this is one advantage of use of biodiesel. The use of biodiesel prevents an increase in carbon dioxide levels, thereby avoiding contributions to global warming. Do we contribute to global warming with the use of biodiesel? It will be minimal to none. The reason is biodiesel will not increase the atmospheric carbon dioxide levels, just like fossil fuels do. It will not. Fossil fuels will increase, but when it comes to biodiesel, it will not increase the carbon dioxide levels. It is a renewable fuel. It can be produced with vegetable oils. So yes, biodiesel is a renewable fuel. We can produce it with vegetable oil. So therefore, it is not going to be a fuel that can be fully exhausted like petroleum fuels. Biodiesel exhibits lower toxicity than petroleum products, and it is biodegradability contributes to reduce environmental impact. So unlike petroleum fuels, biodiesel is biodegradable. So biodiesel contains these ester links that can be broken with microorganisms found in the environment. So therefore, students, this is degradable unlike petroleum products. Biodiesel releases lower amounts of carbon monoxide, particulate matter, cyclic hydrocarbons and aldehyde compared to conventional petroleum fuels. Now petroleum fuels releases all of these, but the release of these types of compounds that takes place through biodiesel is minimal. So therefore, that is considered to be an advantage of the use of biodiesel. Biodiesel releases fewer carcinogenic substances during combustion, making it less harmful to human health compared to the use of petroleum fuels. So the release of carcinogenic substances that takes place due to the burning of biodiesel is less compared to petroleum products. So therefore, students, this is considered to be again an advantage of the use of biodiesel. Petroleum fuels are non-renewable and finite. we can exhaust them. Facing the risk of exhaustion, we can exhaust the petroleum fuels that are out there. In contrast, biodiesel is renewable and can serve as a sustainable fuel source, offering a more environmentally friendly alternative. Eighth point is the high boiling point of biodiesel, approximately around 100 degrees Celsius, reduces its susceptibility to spontaneous ignition, making it safer to store compared to fuels with lower boiling points or lower ignition points. So students, we have a lower ignition point here. They will not easily burn. Drawbacks of the use of biodiesel. The combustion of biodiesel releases less heat compared to petroleum fuels, meaning a larger quantity of biodiesel needs to be burned in comparison to achieve the same energy output. So students, if you compare the energy released by a specific amount of petroleum fuels, let's say petrol or diesel fuel, so the amount of energy released in these fuels is going to be somewhat higher compared to the same amount of biodiesel. So to produce the same amount of energy released in, let's say, petroleum diesel, you will have to burn more amount of biodiesel. The combustion of biodiesel tends to release higher amounts of nitrogen oxide compared to petroleum fuels. Now, with the increased use of biodiesel to produce the same amount of energy that is released by petroleum fuels, the production of nitrogen oxides due to nitrogen in the atmosphere reacting with oxygen in the combustion chamber, the release of nitrogen dioxide into the atmosphere or nitrogen oxides into the atmosphere with the use of biodiesel is higher compared to petroleum fuels. As you know, to get the same amount of energy, we'll have to even burn more amount of biodiesel, and that means when it comes to internal combustion engine, we'll be producing more and more nitrogen oxides. As we know, when we draw air from the surrounding into the engine and when we carry out the burning process, certain amount of nitrogen in the air can get converted into nitrogen oxides. So students, since we have to use more and more of biodiesel to produce the same amount of energy that is produced by a small amount of petroleum diesel, the amount of nitrogen oxides that is produced during the burning process of a larger amount of biodiesel is going to be greater. So therefore, this is considered to be a drawback of the use of biodiesel. Biodiesel typically has a higher freezing point, making it less suitable for the use of cold climates where lower temperatures may cause it to solidify or gel. Right? You might have seen sometimes oils, they solidify in cold environments. Similarly, biodiesel, which is a mixture of methyl esters, fatty acid methyl esters, they have a higher freezing point, not a lower freezing point, higher freezing point. That means at even higher temperatures, like let's say 5 degrees Celsius or let's say 6-7 degrees Celsius, it can freeze, right? So when this happens, compared to petroleum fuels will have a very low freezing point. So therefore, even at low temperatures, the petroleum fuels will remain a liquid. However, biodiesel can solidify, which will make them not very suitable for the use in cold climates. Biodiesel generally has a lower stability, making it less suitable for long-term storage compared to some other fuels. The use of biodiesel lead to deterioration of various components in vehicles such as tubing, gaskets, valves, and parts made with plastic or natural rubber. So, students, this is another major drawback or disadvantage associated with the use of biodiesel, because when you use biodiesel, you will have certain parts of the vehicle that is going to be affected by the use of biodiesel. Sometimes certain vehicles are recommended for the use of biodiesel. At that point, these tubings and gaskets and other components that come into contact with biodiesel are resistant to this type of deterioration. But if you are trying to introduce biodiesel to a normal diesel vehicle, these parts can be affected and can be damaged due to the use of biodiesel. Now we take a look at another renewable fuel source, bioethanol. So bioethanol is used as an alternative fuel. Bioethanol is a renewable fuel, does not significantly contribute to the increase of carbon dioxide levels in the atmosphere when burned, as the emitted carbon dioxide is roughly offset by the plants used in the production. Just like biodiesel, bioethanol also has a closed carbon loop. So therefore, the amount of carbon dioxide that is released into the atmosphere can be captured back again with the plants, that then later on can be used for the production of bioethanol. The standard combustion enthalpy is significantly a high value. So therefore, this is compared to biodiesel, you can see the amount of energy released here is slightly higher. Easily combustible, bioethanol has a relatively low ignition point compared to other fuels, so this can easily be burnt. Correct bioethanol does not contain sulfur, and as a result it does not release sulfur dioxide during combustion. So something that you have to keep in mind is bioethanol should not contain any sulfur, so that would mean there will not be a release of sulfur dioxide into the atmosphere. Bioethanol releases lower amounts of particulate matter, cyclic hydrocarbons, and aldehydes compared to conventional petroleum fuels. Just like biodiesel, the release of these harmful substances into the atmosphere is less when considering bioethanol. Now we look at how we produce bioethanol. Bioethanol can be produced by fermenting palm tree sap, which is commonly referred to as toddy or sugarcane sap. So palm tree sap or sugarcane sap is used. Palm tree sap is commonly referred to as toddy. Apart from toddy, you can use sugarcane sap as well. Sugarcane sap can be used. In this process, yeast enzymes transform the sugar in the presence in the sap into bioethanol through fermentation. In addition to the mentioned plant materials like palm tree sap and sugarcane sap, pineapple, dates, banana, apples also can be used for the fermentation process to produce bioethanol. So students, what we do here is a fermentation that would lead to the conversion of sugars that are seen in these plant materials into ethanol. The sugar that is seen in the plant material is converted into ethanol through a fermentation process. Following fermentation, fractional distillation is employed to extract ethanol with a concentration of 95 to 96%. So we can get ethanol with a concentration of 95 to 96% purity when we carry out fractional distillation. So the related reactions for this particular process is given here. So harvesting palm tree sap, commonly known as toddy, initiates the process of obtaining ethanol. Once collected, the sap, rich in fermentable sugars like sucrose, undergoes fermentation facilitated by yeast and its enzymes, including invertase enzyme and zymase enzyme. So invertase enzyme breaks down the complex sugar into simple forms, and zymase further aids, zymase further aids in the conversion of sugars into alcohol. These actions collectively enable the yeast to transform sugars into ethanol and carbon dioxide. This natural enzymatic process turns palm tree sap, again toddy, into a valuable source of bioethanol, highlighting a sustainable approach in renewable energy production. So you can see here sucrose is broken into glucose by invertase, and then you can see here glucose is taken and converted into ethanol with the use of zymase enzyme. So students, bioethanol can be produced with the use of this process that we have outlined here. So in this particular part, we outline the uses of ethanol, or we can call it bioethanol as well, but we have produced here ethanol with the use of that process we outlined earlier. Ethanol serves as a biofuel. We can use the ethanol that we produced earlier as bioethanol as a fuel. It is used as a solvent for dissolving paints and varnish. Yes, ethanol can be used as a solvent for dissolving many things, including paints and varnish. Ethanol is used as an alcoholic beverage. Yes, we have seen due to the fermentation process, we produce alcohols, and you see that there are many alcoholic beverages that are produced through fermentation processes like this. So in the production of alcoholic beverages, we do use ethanol. It is used in the process of producing certain medicines. Yes, when it comes to producing certain medicines, ethanol is used in the manufacturing process. Ethanol is employed in the manufacturing of perfumes. Yes, students, in the manufacturing of perfumes, ethanol is used. Fragrance compounds or different complexes are dissolved in ethanol, and ethanol will act as a delivering agent, where when you spray the perfume, majority of the fragrance particles are in ethanol, and the ethanol will land on your clothing or whichever the area that you spray your perfume to, and the ethanol will evaporate, leaving behind the fragrance particles. So students, yes, in manufacturing process of perfumes, we do use ethanol. Production of methanol with the use of biomass. Now, earlier on, students, when we were preparing biodiesel, one of the reagents that we used for biodiesel was methanol. So, even methanol, if it is produced with the use of plant material, then at that point, the entire process of producing biodiesel is going to be completely renewable. So we are taking a look at how we can produce methanol with the use of biomass. Methanol is essential to produce biodiesel. Methanol is obtained from the products of petroleum industry. Therefore, biodiesel produced using methanol is not going to be 100% renewable. So, biodiesel produced with the use of methanol, methanol that is obtained from petroleum industry, is not going to make the biodiesel produced 100% renewable, because at the point at which we do not have access to methanol that was produced with the use of petroleum industry, then we can't produce biodiesel. So then what happens? Biodiesel is no longer viable. It is no longer renewable. So to make sure that we do not have to obtain methanol from the petroleum industry, we can turn to the manufacturing of methanol with the use of biomass. Hence, attention is focused on the production of methanol using carbohydrates and other biomasses employing microorganisms. Methanol so produced is called biomethanol. Biodiesel produced using biomethanol is a biodiesel which is 100% based on renewable raw materials. So students, earlier on we observed if we use methanol that we obtain from the petroleum products, then the biodiesel produced is not 100% renewable. But if we can produce biomethanol with the use of biomass, then biomethanol is renewable. So therefore, the biodiesel produced is 100% renewable. So if you add non-volatile plant oils and biomethanol together, when you mix them together, what you get is biodiesel. We will use the catalyst here and the relevant temperatures like 50 to 60 degrees Celsius temperature and the sodium hydroxide catalyst. Now students, we come to the last slide here. So we again revert back to how biodiesel was produced. Biodiesel is produced from the triglycerides present in plant oils. As I mentioned earlier, plant oils contain both free fatty acids and triglycerides, mostly triglycerides. There will be a small amount of free fatty acids as well. So what contributes to the production of biodiesel is mainly triglycerides. The reaction that converts fatty acids of these triglycerides into methyl ester is referred to as trans-esterification reaction. So we have a triglyceride. Triglyceride is where fatty acids are connected to a glycerol to form triglyceride. So you have ester linkages as I have indicated before, right? So each triglyceride has 3 ester linkages. And when we are carrying out the reaction of producing biodiesel, what happens is these ester linkages are broken and another alcohol part is attached to the carboxylic acid part or the fatty acid part of the triglyceride. So students, when that happens, what we have essentially done is convert one type of an ester into a different type of an ester. So therefore, that is known as a trans-esterification process. And what you form here is fatty acid methyl esters. We have long chain fatty acids. Earlier on they were connected to glycerol. Now we break that ester bond and we bring methanol. So then what happens? We will form a methyl ester. We call them fatty acid methyl esters. So students, fatty acid methyl ester mixtures are known as biodiesel. FAME is the abbreviation for the products that are formed here. Here one ester is converted to another ester. Sodium hydroxide solution is used as the catalyst. We learned about this earlier. Biodiesel and glycerol formed are not mixing with one another, so they are immiscible and separate out into 2 layers. The main byproduct of this production or process is glycerol, also referred to as glycerine traditionally. Hence, biodiesel is a mixture of several methyl esters of fatty acids. Biodiesel that has low density floats on the glycerol layer. So students, when you are preparing biodiesel, we showed earlier, you take vegetable oil which is yellowish in color, and then when you add the sodium hydroxide and methanol mixture and continuously stir it at around 50 to 60 degrees Celsius temperature, what happened? We saw this yellowish color in the vegetable oil turn somewhat yellowish brown color, and we saw the 2 layers start to separate as well. And since the biodiesel has a lower density, the top layer is going to be biodiesel with some impurities in it, right, like diglyceride, triglyceride, and certain amount of glycerol and sodium hydroxide. And then the bottom layer will have mainly glycerol, again with some impurities like methanol and sodium hydroxide. So students, we have these two layers separated out. The top layer is biodiesel, the bottom layer is glycerol. We can very clearly see it here. Now glycerol layer is going to appear in a brownish yellow color or yellowish brown color, right? So you can see glycerol layer is somewhat more darker in color, whereas the biodiesel layer is a bit more clearer. So you can separate them out with the use of a separatory funnel, and we can obtain the biodiesel layer and the glycerol layer separately like so. So biodiesel obtained after heating and removing the methanol is given here. So if you want to remove the excess methanol that is present here, you can heat the biodiesel layer. Then what happens? The methanol impurities that are there will be removed. As you heat, the methanol will be removed. If you want to further purify it, you can wash the biodiesel with water. You can wash the biodiesel with water, and then after washing and removing water, there might sometimes be a certain amount of water or moisture that is sticking to the biodiesel. To remove that, you can again heat the biodiesel and remove the water as well by heating. So students, this concludes the theory parts revolving around our experiment number 43. I hope you have obtained good enough understanding about all of the theory that is associated with biodiesel. So now it is time for us to move on out of our classroom and into the lab and actually conduct this experiment and produce biodiesel. Let's move on to the lab. GCE Advanced Level Chemistry Practical Series Experiment number 43, Preparation of Biodiesel. In this experiment, we aim to provide you with the necessary knowledge on how we can prepare an environmentally friendly liquid fuel source, which is biodiesel, and we are going to try and understand the advantages that come along with the use of biodiesel. Now, let's move on to identifying the equipments and the reagents we will be using for this experiment. Students, to conduct this experiment, we will be needing the equipment and the reagents we have here. Starting with the reagents, we will be using vegetable oil, sodium hydroxide pellets, methanol, Erlenmeyer flask, 250 milliliter Erlenmeyer flask. We'll be using beakers, measuring cylinders. Apart from that, to measure the temperature, we'll be using a thermometer. To measure the mass of sodium hydroxide we'll be using watch glasses and spatula. We'll be using a separation funnel, or we call it a separating funnel as well. So this funnel is used to separate out the two layers that are formed towards the end of this reaction. The product, biodiesel, that is formed is not going to be soluble in the aqueous layer, and we are capable of separating out the two layers with the use of a separation funnel. And then we have our digital balance, which we will be using to measure the mass of sodium hydroxide that is needed. We have a heating setup here. We will be using a tripod with a speed burner. So we will be using this setup to heat up the reaction mixture. And then we have a retort stand with a holder for our separation funnel. So when we are separating the two layers, we will be using this setup to hold the separating funnel. Now, we have identified the equipment and the reagents we need for this experiment. So all that is left for us to do is moving on to actually conducting the experiment. Let's move on and start our experiment. Students, now we are going to be producing biodiesel here. So before we start producing biodiesel, let's learn a little bit about biodiesel. So biodiesel is going to be produced with the use of a renewable source, which is plant oils. We will specifically be using non-volatile plant oils here. And when you take plant oils, students, you have triglycerides in the plant oils, and apart from the triglycerides, you will have free fatty acids. So this is a very important point here. So you have to keep this in mind. Plant oil usually has triglycerides along with a certain amount of free fatty acids. Now, a triglyceride is consisting of a glycerol molecule forming ester bonds with long chain fatty acids. So, when it comes to our triglycerides, we have 3 ester linkages or 3 long chain fatty acids forming ester bonds with the triglyceride or with the glycerol molecule. So, when we are trying to form biodiesel, all that we are doing is we are changing this ester or the triglyceride that we have into a different type of ester. We say we are trying to form methyl esters. So, when you are trying to do that, we will be using sodium hydroxide as a catalyst. And this process of converting triglycerides into fatty acid methyl esters is referred to as a trans-esterification process. This is a type of a reaction that is referred to as a trans-esterification process. So, when you are doing this, we use sodium hydroxide as a catalyst. So, if you have free fatty acids in the ester, sodium hydroxide can react with these free fatty acids and can form sodium salts of the carboxylic acid. So, if you consider the free fatty acid to be an RCOOH compound, after reacting with sodium hydroxide, it will get converted into RCOONA, which is actually soap. So, students, this particular reaction that may take place would lead to the reduction in the catalyst sodium hydroxide and might hinder the process of manufacturing biodiesel. So, the oil that you take, in this case the vegetable oil that you take, should have a very low amount of free fatty acids. To be exact, you have to make sure you have less than 2% of free fatty acid by mass. Or in other words, you can say the acid value of the oil should be less than 0.1 milligrams of potassium hydroxide per gram of oil. So, what is this acid value? Acid value is the amount of potassium hydroxide that is needed in milligrams to neutralize the free fatty acid content in 1 gram of oil. So, if you take 1 gram of oil, there will be a certain amount of free fatty acids. These free fatty acids can be neutralized by the addition of potassium hydroxide. So, the mass of potassium hydroxide needed to neutralize the free fatty acid in 1 gram of oil should be less than 0.1 milligrams. So, this is the understanding you should have going into the production of biodiesel. However, students, when it comes to industrially manufacturing biodiesel, there are about 5 steps. First step being treating the oil, removing all impurities from the oil and saponifiable and non-saponifiable components and pigments from the plant oil. And then secondly, we can move on to preparing our catalytic mixture, the mixture of sodium hydroxide and methanol. And thirdly, we can mix the vegetable oil with the catalytic mixture and allow the reaction to take place. At this point, there will be 2 layers formed. And the fourth step would be separating these 2 layers. And fifth step is further purification of our biodiesel layer by sending water and dissolving out all the glycerol that is formed. And when it comes to purification, you have to remove methanol also that is present in biodiesel. If you use excess methanol, that is going to be present in the biodiesel as well. So through heating, you can remove methanol as well. So these 5 steps are usually seen when you are preparing biodiesel industrially. In this experiment, we are going to follow only a few steps to observe how biodiesel can be prepared in a lab setup such as this one. So now let's first move on to measuring sodium hydroxide that we need and start our practical. Now we will take our watch glass, and before placing the watch glass on our digital balance, we turned it on. So we will place the watch glass on our digital balance like so, and we can remove the mass of the watch glass from the digital balance reading by tearing the balance. So we have pressed the tear button. Now we have removed the mass of the watch glass from the digital balance reading. Then we have here sodium hydroxide. So in this container, we have sodium hydroxide in the pellet form. We will take a small amount of sodium hydroxide and place it on our watch glass here. Keep in mind, students, they only need you to use 0.5 grams of sodium hydroxide. We have 0.49 grams of sodium hydroxide. Now students, we have measured 0.49 grams of sodium hydroxide. If I had added one more pellet, it would have gone well above 0.5. So to avoid doing that, we will use 0.49 grams of sodium hydroxide here. And then we will transfer this into our Erlenmeyer flask. We will no longer need the balance. We can remove it as well. So in this Erlenmeyer flask, we have our sodium hydroxide, and we are going to dissolve it not with the use of water. We are going to dissolve it with the use of methanol. So we have our methanol here. We can use about 20 milliliters of methanol to try and dissolve this sodium hydroxide. So we have measuring cylinder. Let's take about 20 milliliters. Of methanol. So we have taken about 20 milliliters of methanol, and we are going to try and dissolve the sodium hydroxide in this methanol. And keep in mind, students, this is what we do when we are preparing our catalytic, where we have our sodium hydroxide dissolved in methanol. So let's take our methanol, add a small amount of methanol, and let's try and dissolve the sodium hydroxide. By stirring it, you will be able to dissolve the sodium hydroxide that we have here. We'll add the whole of 20 milliliters of methanol into the Erlenmeyer flask, and we can continuously stir until the sodium hydroxide that we have here completely dissolves. Alternatively, we can use a stirring rod as well. or we can stir the contents in the Erlenmeyer flask by swirling the Erlenmeyer flask around. You might observe little by little the sodium hydroxide starts to dissolve. Now we will completely dissolve this and keep it prepared for the next step in this experiment. Now students, we have dissolved our sodium hydroxide in methanol. It is important to note that we didn't use water to dissolve sodium hydroxide. We used methanol to dissolve the sodium hydroxide we measured into this Erlenmeyer flask. It might take a while when you are conducting the experiment to dissolve sodium hydroxide in methanol, but if you are patient enough, it will get dissolved after some time. After that, we are now moving on to taking some vegetable oil into 250 milliliter beaker, and we are going to heat it to 40 degrees Celsius. So to measure the amount of vegetable oil we need, we will be using a measuring cylinder, and we have our vegetable oil here. Students, as I mentioned before as well, the first step when it comes to preparing a biodiesel is to treat the vegetable oil or the plant oil that you're using before using it for this particular reaction. So usually the plant oils that we obtain will have a lot of other material than just the oils we need, such as different types of pigments and sometimes solid particles and free fatty acids. Other non-certifiable compounds will be there. To remove these compounds, you can actually send the oil through activated fuller earth at 90 degrees Celsius. So when you send it, majority of these compounds will get removed from the oil, and you can use the resultant product to carry out an experiment like this. So we have our vegetable oil here. We will measure 100 milliliters of our vegetable oil. We have taken a little bit extra. Now students, we have measured 100 milliliters of the vegetable oil that we are going to be using for this experiment. Let's transfer this amount of vegetable oil into our beaker here. It will take some time for all of the oil to be transferred into our beaker. After transferring all of our vegetable oil into our beaker, we are now going to heat this vegetable oil until it reaches a temperature of around 40 degrees Celsius. And at that point, we are going to add the vegetable oil to our catalyst mixture that we prepared earlier, and the entire reaction mixture is going to be kept between a temperature of 50 to 60 degrees Celsius. So let's place this vegetable oil on our tripod here like so, and let's start heating it until it reaches a temperature of 40 degrees Celsius. We can use a thermometer to measure the temperature that it is currently at. Currently, it is at a temperature of 32 degrees Celsius. Now students, we have heated this oil to 40 degrees Celsius. So we have turned off our spirit burner and the temperature at this point is 40 degrees Celsius. Now, since we have measured the temperature, we can remove our thermometer and we can move on to adding this oil into our catalyst mixture that we have in front of us. So we prepare this catalyst mixture by adding sodium hydroxide and methanol together. Now we will be adding the oil that we heated up into our sodium hydroxide and methanol mixture. And after adding these two together, we have to continuously stir until two very clear layers form. And students, to speed up this reaction, we can heat this mixture up to a temperature between 50 to 60 degrees Celsius. So let's light up our spirit burner once more and we'll heat this mixture, and if it gets too hot we will remove this mixture from the setup, and again after it cools down we will heat it again until we can see very clearly two layers being formed. Let's measure the temperature of this mixture. The temperature of this mixture is somewhat above 50 degrees Celsius. Now students, keep in mind to take the Lidmeyer flask off of the heat every once in a while, because we need the temperature to be maintained between 50 to 60 degrees Celsius. After the system reaches 50 degrees Celsius, you do not need to keep it for a long time on the heat. So you can remove it and continue to stir off of the heat. So when you are stirring, what you're trying to do is making sure the two layers, which is the oil layer and the alcohol layer, mix really well, as these two layers are usually not very miscible. So to facilitate the reaction, we have to continuously stir until we see the formation of two layers form again. So when you see the formation of two very distinct layers, then we can be certain that the biodiesel has been produced. Students, now we have been stirring this mixture for a while. To make sure the reaction happens efficiently, we have to keep stirring until two layers start to appear again. So you can see here in this reaction mixture, there is formation of two layers again, and the above layer is our biodiesel layer, and at the bottom we have our sodium hydroxide, methanol and glycerol layer. So right now what you see here is the formation of two layers. So right now what you see here is the formation of two layers when you are carrying out this reaction. So we can continue to further mix this to make sure if there are any other excess amount of triglycerides and the catalyst mixture that still can react to one another present in this mixture. To facilitate them reacting, we can continue to stir it for a while, and after that we are going to very clearly observe the two layers formed, and then transfer this mixture to a separation funnel or separatory funnel. And then we will separate out the top layer. We will again observe the formation of two layers after mixing it for a while. Now students, we have mixed this reaction mixture and we have allowed it to settle for a while so that we can observe the two layers very clearly, because it takes a while for this layer separation to happen. Now if you observe here, we can see two layers here, and on the above layer is where we will find our biodiesel. Biodiesel is a mixture of fatty acid methyl esters. So we have different types of fatty acids undergoing trans esterification reaction and forming fatty acid methyl esters, which is normally abbreviated to FAME. So in this fatty acid methyl ester mix that we have here as the biodiesel, we have different types of carboxylic acids such as lauric or myristic, palmitic and stearic acids. So these types of different acids will undergo trans-esterification process and form fatty acid methyl esters, and this mix of fatty acid methyl esters will have different number of carbon atoms, or different types of methyl esters are present here. Majority of the methyl esters will have a carbon atom number ranging from around 12 carbon atoms all the way up to 18 carbon atoms. The biodiesel we have here is going to contain fatty acid methyl ester mix, which will have a different number of carbon atoms ranging from 12 carbons all the way up to 18 carbons. And apart from the biodiesel we have here on the top layer can also contain small amounts of unreacted triglycerides or diglycerides can be there. Apart from that, small quantities of glycerol also might be present in the top layer, which is the layer that contains mainly biodiesel. And on the bottom layer, you are going to have mainly glycerol, unreacted or excess methanol that we used along with the catalyst. So on the bottom layer here, those are the main compounds that you can find, mainly glycerol, unreacted or excess methanol that we added, and sodium hydroxide will be found on the bottom layer. So now we can move on to transferring this mixture, or two layers rather, into our separating or separatory funnel. So we have our separatory funnel or separation funnel. We can make sure the tap is all the way closed and then transfer our two layers of biodiesel and glycerol into our separatory funnel. So I have made sure that this tap is fully closed. Now all that is left for us to do is transfer these two layers onto our separatory funnel and then separate out the two layers. So we will bring this setup over here, and we can now remove this lid and transfer our biodiesel and glycerol layers. We will do it very slowly. So when you're transferring these two layers, we have to be very slow about it without causing much agitation. We have to transfer it into our separatory funnel. When adding these two layers into our separatory funnel here, there could be some agitation that take place. So we will allow this mixture to settle in the separatory funnel for a while before we move on to separating the two layers into two separate beakers. Students, in the previous part of this experiment, we reacted methyl alcohol with sodium hydroxide, and then to that mixture we added vegetable oil, and then we allowed the reaction to take place in this reaction mixture, and later on we saw the formation of two layers, and then we transferred this mixture onto a separation funnel. So in the separatory funnel, we could not very clearly observe the interface between the two layers because these two layers were still settling down and we couldn't very clearly observe the two layers separately. But now we have allowed the two layers to settle for a while and we can very clearly observe the two layers that are formed here. And the interface between the two layers is also very clearly visible here. On top, you have your biodiesel layer. As I mentioned earlier, this contains a biodiesel, which is fatty acid methyl esters. So these fatty acid methyl esters might contain a varying number of carbon atoms, ranging from anywhere between 12 to 18 carbon atoms. And apart from that, this top layer also might contain triglycerides that have not reacted, diglycerides, and small quantity of glycerol. However, on the bottom layer, what you mainly find is the glycerol that has separated out from the top layer. You have glycerol here. Apart from that, the excess methanol that we have added to the reaction mixture will also be found along with some sodium hydroxide. So we can very clearly observe the two layers. Now we are going to separate the two layers with the use of our separatory funnel. So we have a beaker here labeled glycerol because this bottom layer that we have here mainly contains glycerol. So we can open the tap and allow the glycerol layer to get collected into our beaker that is labeled glycerol. So as soon as all of the glycerol layer is taken into our beaker here, we can close the tap. At that point, only the top layer will stay or remain in our separatory funnel. And then we can remove that layer into another beaker so that we can obtain our biodiesel separately. So let's open this tap and slowly remove our glycerol into this beaker, and we have labeled it glycerol as well. As soon as this biodiesel glycerol interface comes to where the tap is, we will close the tap and to a separate beaker, we will collect our biodiesel. Now, students, you have to keep in mind, glycerol is a product that is used in many industries, especially the cosmetics industry. Now, as the glycerol biodiesel interface gets close to where the tap is, we will get ready to close this tap, making sure we don't allow any biodiesel to get into our glycerol that we have here. Now, students, we have separated out our bottom layer into a beaker. So what we mainly have here is glycerol. There will be small amounts of excess methanol that we used. Apart from that, a certain amount of sodium hydroxide might also be present here. However, main component that you find in this bottom layer of the two layers was glycerol. So as I mentioned earlier, glycerol is a widely used compound, especially in the cosmetic industry or skincare industry. It is used quite often. So this is a very valuable product for those industries that actually use glycerol. Now, let's move on to collecting our biodiesel layer into a separate beaker. So we have here a beaker labeled biodiesel. So what we have here on the top layer out of the two layers is mainly biodiesel. So let's collect our biodiesel into this beaker. And now, students, we have separated out our biodiesel layer into a separate beaker. So we have diesel here, we have biodiesel, and the vegetable oil that we used to form our biodiesel. Students, when we were talking about biodiesel, we learned biodiesel is basically a mixture of fatty acid methyl esters. So we have long chain fatty acids that are reacted with methanol to form fatty acid methyl esters. So these long chain fatty acids were originally found in triglycerides. So they had ester bonds with the glycerol molecules forming triglycerides. And when we added sodium hydroxide and methanol mixture to these triglycerides, we saw a trans-esterification took place to form fatty acid methyl esters. So this is a mixture of fatty acid methyl esters that we consider to be our biodiesel. And we have diesel here. Diesel is mainly a mixture of hydrocarbons. So majority of the hydrocarbon molecules that we find in diesel have a varying number of carbon atoms, mainly ranging from somewhere around 10 to 20 carbon atoms in these hydrocarbons. So diesel and biodiesel are two different compounds, but they do have similar properties, such as both of them can be used to make the engine function. Now, students, again, for comparison, we have vegetable oils to prepare our biodiesel, and we have the biodiesel we prepared. And apart from that, we have diesel that is normally used in a diesel engine. So now let's take a small piece of filter paper and in we'll dip it in biodiesel and set it on fire to observe how the combustion of biodiesel take place. So we will be using a pair of tongs to hold our filter paper, and we will dip it in the biodiesel, and then we'll move a step back and we will set the filter paper on fire. The reason for moving a step back would be because we are having a few different fuels here, and we wouldn't want anything to catch fire. So as a precaution, we can take a step back and move slightly away from these fuels and conduct this experiment. So let's dip this filter paper in our biodiesel, and we will move a step back and we will set this filter paper soaked in biodiesel on fire. As you can see, students, when you set the filter paper soaked in biodiesel on fire, it easily catches fire and burns for a little while longer than a usual filter paper would. So now let's move on to another comparison. Now students, we have in front of us vegetable oil, biodiesel and diesel. And in 3 petri dishes, we have one piece of cotton wool. We are going to dip each of these cotton wool pieces in diesel, biodiesel and vegetable oil separately, and we are going to observe how these cotton wools will burn when we set them on fire. So first, let's take the first cotton wool piece and we'll dip it in vegetable oil. Now, after wiping the tips of the tongues, we will be moving on to the second cotton wool. Now we'll take the second cotton wool piece and we will dip it in our biodiesel. After wiping the tongues, pair of tongues that we're using, we will now pick up the third cotton wool piece and we will dip it in diesel. Now students, before we move on to setting these cotton wool pieces on fire, let's remove these biodiesel, diesel and vegetable oil beakers away from the petri dishes, as diesel and biodiesel may catch fire. We will move them away and we can bring each of these petri dishes here and now set them on fire. Now students, what we have here is a piece of cotton wool dipped in vegetable oil. What we have in the middle is the biodiesel that we formed, and on the left hand corner what we have here is a cotton wool piece that is dipped in diesel. So now let's set each of them on fire and observe how they burn. Now students, this is our vegetable oil. We have our biodiesel here, and on the left hand corner we have our diesel. So now students, as you can see here, when it comes to the vegetable oil, you don't see a huge flame produced. When it comes to our biodiesel, we can see it is burning considerably well, but not as much as diesel. And when diesel is getting burned, you can see the formation of a black smoke due to the unburned carbon that we see here. When diesel is getting formed, you can see the formation of the black smoke. So we can be certain that we have produced biodiesel. As you can see, the biodiesel is burning way better compared to the vegetable oil that we use to form this biodiesel. Now let's turn these off, as we are collecting a lot of smoke in the lab. We will turn off each of these uh, flames that we have here. So this is the biodiesel flame. We will observe it for a little while longer. As you can see, it burns really well for quite some time. A usual cotton wool piece wouldn't burn for this long without a fuel helping it to burn for this long. I hope you have observed the flame that was created with the use of biodiesel. Now we'll go ahead and we'll turn it off. With that, students, we can conclude our experiment. Keep in mind, students, industrially, when you're preparing biodiesel, we have around 5 different steps that I mentioned earlier. You will be pre-treating the oil and purifying it a little bit, and you will be then forming your catalyst mixture. And on the third step, you'll mix the catalyst mixture and your vegetable oil and allow the reaction to happen. In the fourth step, you will separate the two layers, and the bottom layer would contain glycerol and the top layer would contain biodiesel. And after the separation has happened, in the biodiesel layer, we will further purify it and remove the excess methanol that you might find in the biodiesel, and apart from that, there will be small trace amounts of glycerol that you might find. So you can wash the biodiesel with water, and to remove the methanol, you can heat the biodiesel. However, you have to keep in mind, after the preparation of biodiesel, there's usually a purification step. In the lab, when it comes to conducting this experiment, we wanted to observe simply the formation of biodiesel, so we didn't go along with the purification process of biodiesel. So with that in mind, we can conclude our experiment and move on to our more important theory parts and questions revolving around this experiment number 43. Now students, in the first part of this experiment, we looked at the theory parts revolving around practical 43, preparation of biodiesel, and then we moved into the lab and actually produced biodiesel, and now we will be discussing some questions revolving around the production of biodiesel. So let's take a look at the first question. So in the first question we have this question: the reaction for the preparation of biodiesel from plant oil is given below. Right, we can see a triglyceride with different hydrocarbon chains in the fatty acid given here. What can be used to catalyze this reaction? What is the reaction type observed in this reaction? Give reasons as to why biodiesel is considered a green fuel compared to other petroleum fuels. If sodium hydroxide was used instead of methanol, apart from the product C, which is this, what are the three other products that would be formed? State those three products. What is the name of the reaction that takes place in the D part of this question? What is the industrial name given to the product formed in part D? And write the IUPAC name of the product C and write the uses of product C. So let's answer these questions so that we can discuss some additional details revolving around this question. So we have this reaction, you can see we have the triglyceride and we have methanol here, and we can very clearly see a trans-esterification reaction has happened here and produced fatty acid methyl esters and glycerol. What can be used to catalyze this reaction? What can be used to catalyze this reaction? We can use sodium hydroxide. We can use NaOH. NaOH, sodium hydroxide. We can also use potassium hydroxide. So these are some of the catalysts we can use. Sodium methoxide also can be used as another catalyst. So these are some of the catalysts we can use for this reaction. What is the reaction type observed in this reaction? So in this reaction, what is the reaction type that we can see? We just disclosed the name a little while ago. What is the reaction that is happening? These methyl groups are replacing this glycerol that is seen in the triglyceride. So each of the fatty acid parts of the triglyceride is now attached to a methyl group. Over here, one ester has gotten converted into another ester. So what is this? This is known as a trans-esterification process or trans-esterification reaction. Trans-esterification reaction or process. We can move on to the next question. Give reasons as to why biodiesel is considered a green fuel compared to other petroleum fuels. So students, we know other petroleum fuels are finite. They can be exhausted. But when it comes to biofuels or biodiesel in this case, it's a renewable fuel that is made with plant oils. So we can write it is a renewable fuel produced with non-volatile plant oils. Therefore, it does not contribute CO2 levels in the atmosphere. So students, unlike fossil fuels, which is not a renewable fuel source, when fossil fuels are burnt, we learned it releases carbon dioxide, and that carbon dioxide is not going to be fixed into fossil fuels in a short period of time. However, since biodiesel is a renewable fuel source, it actually, the carbon dioxide that is released through the burning of biodiesel can easily be fixated into plant materials and removed from the atmosphere in a considerably short period of time. Apart from that, there is no sulfur present in biodiesel. Therefore, there won't be sulfur dioxide emissions. So the environmental impact that comes through sulfur dioxide emissions will be minimal with the use of biodiesel. As you know, petroleum fuels contain certain amount of sulfur, so due to this, when petroleum fuels are burned, sulfur dioxide can enter the atmosphere, which could have significant environmental impacts. So these are some of the reasons. Apart from that, we can list down the fact that the release of cyclic hydrocarbons, aldehyde groups, or carcinogenic substances that are released into the atmosphere due to the burning of biodiesel is less. Right, this is again another advantage for the use of biodiesel. There are many. If you have listed down a few, that is sufficient. So students, we have now disclosed some reasons why we consider biodiesel to be a green fuel compared to petroleum fuels. If sodium hydroxide was used instead of methanol, apart from the product C, 3 other products would be formed. State these 3 products. Now students, we saw earlier on, when this reaction is taking place, we used methanol. Now the question is, instead of methanol, if sodium hydroxide was used instead of methanol, then what are the products that you can obtain here? What are the products that you can obtain here? So then we can see over here, there are R1, R2 and R3 groups in the triglyceride. So we can write the reaction that is taking place. So we have R1 and then CH2 here, and then we have CH here. Again, this is connected to a similar group, but this is going to be R2, and then we have R3. Okay, now all of these are ester bonds. The carbon-oxygen bonds that we have over here are ester bonds. If you add sodium hydroxide, then students, we can expect to obtain R1 COO Na, R2 COO Na, R3 COO Na. So instead of a trans-esterification process, students, what you see here are these 3 products formed, and this is referred to as a saponification reaction. Saponification means the formation of soap. Over here, these sodium salts of fatty acids that we have over here are considered to be soap. And apart from these products, we will also get glycerol. So if I'm following the same way that glycerol is written over here, I can write glycerol like this. just following the same structure. Right, so you have produced soap and glycerol, or in other words, sodium source of fatty acid. So apart from that, glycerol will also be produced. They are asking to state the products. These are the products that are going to be formed. What is the name of the reaction that takes place in the above D part of the question? As mentioned earlier, this is referred to as a saponification. Saponification reaction. Saponification reaction. We will not see a transesterification process if you replace the methanol with sodium hydroxide. What is the industrial name given to the product formed in D? What is the industrial name given to the product formed in D? So what is the product that we have formed here in D? What we have produced is soap. So the industrial name that is given to the product that is formed over here is soap. It's a mixture of sodium salts or fatty acids. So the product that is formed here is referred to as soap. Write the IUPAC name of the product C. So the product C that we have over here, product C that we have over here is glycerol. Product C is glycerol. We'll copy it down here. So we have glycerol, CH2OH, CHOH, and CH2OH. There are three OH groups. Now this is a triol, and we can see to the first, second, and the third carbon, these OH groups are connected. So when you are naming this compound, the name, IUPAC name of this compound is propane, 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 1, 2, 3 dash triol, TRIOL. So this is a triol, and the name is propane 1, 2, 3, 1, 2, 3 triol. This is also commonly referred to as glycerol or glycerine. Glycerol or glycerine, but the IUPAC name is propane 1, 2, 3 triol. Write three uses of the product C. So product C is glycerol. So glycerol actually is produced when you are producing soap. So when you produce soap with the use of plant oils, one of the products is glycerol. But glycerol is a more valuable product compared to soap. So we do not leave all of the glycerol that is formed in this saponification process in soap. We remove most of the glycerol and leave some glycerol in soap. So in the soap manufacturing process, we use glycerol. So why do we use glycerol, or why do we leave some glycerol in soap? It helps retain moisture of the soap, and actually it makes the soap smoother and softer. So one reason is we can write to help retain moisture of soap and to make the soap smoother and softer. Apart from that, we do use glycerol in many cosmetic products like skincare products, lotions. Again, we can see them used in the production of skin care products and other cosmetics. Another use would be the production of nitroglycerin, also known as TNG, also known as trinitro glycerine, TNG. Right, so these are some of the uses of glycerin, students. Apart from that, products like toothpaste also use glycerin. So some of the main uses of glycerin are given here. So now we move on to the second question. So let's take a look at the second question over here. A triglyceride found in a plant oil was heated with excess concentrated sodium hydroxide. Very important. As products, glycerol and 3 other substances were formed. So we have the triglyceride here indicated as A. And you can see the fatty acid chains here as well. What are the products that are formed in this reaction? That's the question number 1. Write the uses of the products that are formed alongside glycerol. We know when we add excess sodium hydroxide, one of the products that we form here in the presence of excess sodium hydroxide, or when you only have sodium hydroxide, instead of having a transesterification process, what you have is a saponification process. So you produce soap. So we know that. So the answer to the first question, what are the products that are formed in this reaction? One is glycerol, the other one is soap. Write the uses of the products that are formed alongside glycerol. So apart from glycerol, there will be other products that are formed. What is the use of it? So what is the use of soap? As a washing agent. What is the IUPAC name of glycerol? We have already answered a similar question to this. The compound A was added with methanol and sodium hydroxide and was heated to 60 degrees Celsius. What are the products that would be formed in this reaction? So then we should be able to write the transesterification reaction and the products. What are the uses of main product that is obtained in the reaction mentioned in part D? So in the transesterification reaction, what is the main product? You can see in the transesterification process of a triglyceride obtained from a plant oil, the main product is going to be fatty acid methyl esters, which is commonly known as biodiesel in a manufacturing process like this. So that is the main product. What is the name of the reaction that is taking place in part D? As I mentioned earlier, transesterification process. Does the product that is formed in the initial reaction mentioned in part A dissolve in water? Give reasons. So we are going to take a look at the answer to this question in a second. if calcium chloride or magnesium chloride is added to the aqueous system mentioned in the above G part, what can be observed? Explain with reactions that are taking place. So this part again is a part where we need to write equations and provide expressions with. So I will explain that part when we get to it. So let's answer the first part. What are the products that are formed in this reaction? We have over here a reaction that is taking place, right? We are reacting it with sodium hydroxide. So what are the products? The ester bonds will break and will be forming these products. Over here, glycerol will be formed, CH2OH, CHOH, and again CH2OH will be there. Keep in mind each of these carbons are bonded to one another, right? So this is glycerol. Apart from that, we are going to see different sodium salts of carboxylic acids or sodium salts of fatty acids will be formed. This is one of the sodium salts of a fatty acid. Sometimes it is also written sodium 1 plus and O minus, but keep in mind these ions are staying together, so we can also write it this way. And then we have another sodium salt of a fatty acid. Sodium and oxygen, here there's an ionic connection, sodium 1 plus and O minus is there. CH2 then CH double bond CH, CH2 CH3. This is the second product. This would be the third. So these are the three sodium salts of fatty acids that are formed in this particular saponification reaction that is taking place. Apart from that, you will be forming glycerol as well. Write the uses of the products that are formed alongside glycerol. So we have to write the use of the product that is formed apart from glycerol. So glycerol's uses are listed earlier. We know what glycerol is used for. What is the sodium source of the fatty acids? What are the uses of these? As a washing agent, it is used as a washing agent. We can use soap as a washing agent. Actually, and these sodium salts of fatty acids also can be used as surfactant. Can be used as a surfactant. What is the IUPAC name of glycerol? So again, this is something that we have already looked at earlier, but this question also brings us to the same question. What is the name of glycerol in the IUPAC naming system? Answer was propane 1,2,3 triol. Propane 1,2,3 triol. The compound A was added with CH3OH and NaOH and was heated to 60 degrees Celsius. What are the products that would be formed in this reaction? So again, students, we know glycerol will be formed. So we can write CH2OH, CHOH and again CH2OH. And apart from that, all of the other products here, there will be three other products that are formed, and they are going to be fatty acid methyl esters. So we are going to have CH3 groups. So for all of these fatty acid methyl esters, this section that I'm drawing would be common. This section that I'm drawing, or this part of the molecule, would be common. So I can write that part. Each of the fatty acid methyl esters will have this. So now let's take a look at the main molecule over here. So earlier, when sodium hydroxide added to the main triglyceride, these were the products that were formed. CH214 CH3, CH27, and then carbon-carbon double bond group here, and then again CH27 and CH3, and then CH212 and CH3. So let's copy actually these parts to our answer on the question that we were doing earlier. So CH2, 14, CH3, CH2, 7, CH, carbon-carbon double bond. CH2, 7, CH3, and then we have CH2, 12, CH3. So these were the main groups. We'll double check whether the answer is correct. We'll now refer to the molecules that we have over here: CH214 CH3, CH27 CH double bond CH and CH27 CH3, along with these will be produced CH212 CH3. So we do have the same R groups. Those are referred to as the R groups. So the R groups are the same here as well, right? So in these esters, the alkyl groups have all changed to methyl alkyl groups. So we have methyl esters of these fatty acids. So these are known as fatty acid methyl esters. These are known as fatty acid methyl esters. So these are the main products. And these three over here are fatty acid methyl esters. Also referred to as FAME. This is the abbreviation for the term fatty acid methyl esters. So a mixture of fatty acid methyl esters are considered to be known as biodiesel. Actually, a mixture of fatty acid methyl esters are referred to as biodiesel. So this is the answer to the question that was asked. These are the products. What are the uses of the main product that is obtained in the reaction mentioned in part D. So the main product is biodiesel. So what is the main product? Can be used as a liquid fuel. It can be used as a liquid fuel. If you want to add more details, you can say this can be used as a renewable and sustainable liquid fuel. What is the name of the reaction that is taking place in part D? Now students, triglycerides are a type of an ester, and when we added methanol and sodium hydroxide, these esters, they got converted into methyl esters. So what type of reaction took place here? We refer to the type of reaction as a trans-esterification reaction. So students, over here, what you see is a trans-esterification reaction. Trans-esterification reaction. Does the product that is formed in initial reaction mentioned in part A dissolve in water? Give reasons. So now students, we'll take one of the products. We'll take one of the products that is formed. So one of the products was this CH3, CH2. This was one of the products that were formed. And we had C, Na, the sodium salt of a carboxylic acid, or sodium salt of a fatty acid. So this also can be written as, this section can be summed up as an R group, R, C double bond O, and then O, Na. So students, this section over here that we have is a hydrocarbon section. We'll highlight it in different color. This section is a hydrocarbon section. Mainly hydrocarbon is here, present here. It's a hydrocarbon section. And then we have a carboxylate anion group along with a sodium 1 plus ion. So this part is, as you can see, they have charges, as well as you know, oxygen is going to be partially positively charged here. So this section of the soap molecule is water soluble. This section is water soluble. Also referred to as a hydrophilic section. This section is hydrophilic. And this hydrocarbon section is not soluble in water, so we refer to it as a hydrophobic section. So you can see in the in the soap that we have produced over here, one section is soluble in water, whereas the other is not very soluble in water. However, due to the presence of this COONA group, the entire soap molecule that you see over here is going to be soluble in water. And you know from experience, through experience, that soap, it does dissolve in water. Certain amount of soap will dissolve in water. So students, the answer is yes, soap will dissolve in water due to COONA group being soluble in water. right? So the R group is the hydrocarbon group, which is not going to be soluble. However, the other group is soluble in water. So students, when it comes to the washing that is involved when using soap, what happens is we can indicate the soap molecule like this. Now a soap molecule has a hydrocarbon chain and a COO minus group along with Na plus. So this section is hydrophilic. So we actually say this section is a hydrophilic head section of soap. Hydrophilic head section of the soap, and the hydrocarbon section. Now we can see the skeletal structure of hydrocarbon. So this hydrocarbon section of soap is referred to as hydrophobic tail. Hydrophobic tail. Hydrophilic head and then hydrophobic tail. So when you are trying to wash off dirt or greasy substances, the hydrophobic tail easily dissolves in these things and cover the entire surface of the grease or the dirt with soap, and the washing is made easy at that point. So let's take an oil droplet here. Now this is going to be mainly soluble in a hydrocarbon group of the soap rather than the hydrophilic head part of the soap. Or in other words, oil droplets are not very soluble in water. However, this organic part of the salt is going to be able to easily dissolve in water, easily dissolve in the oil droplet. So students, if this oil droplet dissolves a section of the hydrophobic tail of soap, at that point you can see you are only going to have the hydrophilic heads exposed to the surface. Now the oil droplet is completely surrounded by soap molecules, and the hydrophobic tails of the soap molecule is dissolved in the oil droplet, and this causes only to expose the hydrophilic heads of the soap molecules to the exterior. So these hydrophilic heads will now make it possible for this entire thing to dissolve in water, because the exterior is soluble in water. So the whole this tiny droplet of oil is now completely covered with hydrophilic heads on the surrounding or on the surface of the oil droplet. So the oil droplet is now soluble in water. So this action is also referred to as the action of surfactants, and soap is also referred to as a surfactant because when you have two things that does not mix with the use of a surfactant, we can actually make these polar, non-polar two layers mix with one another. So this is the action of soap when washing dirt or when washing oily substances or greasy substances from your hand. So it will first break into small oil droplets, the dirt, and then it is going to be covered with soap molecules like this, which will only expose the hydrophilic head areas of the soap molecule out to the exterior, which will make it soluble in water, because these heads are soluble in water, and the non-soluble parts, actually the hydrophobic part of the soap, is dissolving the oil droplet. Right, students? So this is what happens when you're washing off dirt that is difficult to be washed off just with water. Right, so now we can move on to the next part. If calcium chloride and magnesium chloride is added to aqueous system mentioned in the above G part, what can be observed? So now in this question, what is asked is, what happens if magnesium chloride and calcium chloride is present in an aqueous system where soap is dissolved? So in other words, magnesium chloride and calcium chloride students introduce magnesium ions and calcium ions into the aqueous medium. So in the aqueous medium that contains magnesium and calcium ions, what happens if you try to dissolve soap? Now magnesium and calcium ions are present in hard water. So have you ever experienced what happens when you try to wash your hands using hard water and soap? Will the washing action be there? Will you observe soap suds? Will you observe the formation of bubbles when you use hard water to wash your hands with the use of soap? You will observe that when you use hard water that contains calcium and magnesium ions, the soap will not dissolve very well in water like that, and the action of soap will not be observed. Explain with reactions what is taking place. So when you react soap, which is indicated like this, we can actually write the formula of soap this way as well, COONA. With magnesium chloride So students, this product over here is water soluble. This reactant actually, soap, this is soap. And what we form over here is produced as a precipitate. And this is often referred to as soap scum. It's a precipitate that is going to be observed due to the fatty acid anion combining with magnesium or calcium ions. So the washing action of soap is no longer going to be observed. So if you write the same reaction for calcium chloride, we can observe the same thing happening. You will observe, we will form soap scum here as well, and sodium will be displaced, or sodium will be going off as sodium chloride. So students, here also what you have formed is soap scum. So this soap scum that is formed is not going to be soluble in water. It is going to be present as a precipitate, and due to that, the washing action of soap is not observed in hard water, because in the presence of magnesium and calcium ions, these precipitates will be formed and soap will be precipitated out as soap scum that is given here. So students, the answer to this question, right, explain the reactions that are taking place. We have given the reactions. What can be observed? The soap will be precipitated out, and what you see here is a white color precipitate that is referred to as soap scum. So now let's move on to the next question. The third question: when vegetable oil is heated to 60 degrees Celsius with methanol while using sodium hydroxide as a catalyst, an ester and trihydric alcohol was formed. Vegetable oil is referred to as X here. You can see the formula or the structure of vegetable oil is given. If vegetable oil is denoted with the letter X, write the equation for the reaction that takes place with methanol and sodium hydroxide. So we have to write the equation. First part. What is the name of the reaction that is observed above in the A part? So what is the name of the reaction? The vegetable oil above is an unsaturated vegetable oil. So they very clearly state it is an unsaturated vegetable oil that contains carbon-carbon double bonds. State the number of carbon-carbon double bonds that is present in one molecule of X. D part. In the food industry, X vegetable oil is transformed into a spreadable solid fat. So the oil is converted into a solid fat. State the chemistry behind this process. And the fourth question, the formula of diesel fuel obtained through crude oil is given here. Write the balanced chemical equation for the complete combustion of this molecule. So we'll start with the first question. If the vegetable oil is denoted with the letter X, write the equation for the reaction that takes place with methanol and sodium hydroxide. So we have the vegetable oil, actually the formula is given here. So what will happen if this particular vegetable oil, C21H39 COO CH2 and then you have C21H39 COO, and again we have the same C21H39. So this is the vegetable oil that we have, and when it is reacted with sodium hydroxide and methanol, so I will write the reactants here. We know sodium hydroxide is and methanol is given, so they are asking us to write the equation. So at that point we'll have to balance it, so we'll write the reactants on the correct place. We'll need 3CH3OH, and sodium hydroxide is going to be used as a catalyst. And the products are going to be, we will have mainly C2139 CH21 C21H39. This is the hydrocarbon part of the methyl ester that is getting formed, and we have COO CH3 now. And since the hydrocarbon part of the fatty acid chain in this triglyceride was the same, we can see C21H39, in here also C21H39. Since the fatty acid hydrocarbon chain of this triglyceride was the same, we can expect the same methyl ester to be formed here. So we can directly write 3 here. 3 C21H39 and COOH. Now apart from this, there will be another product that is formed. That is going to be our glycerol, CH2 OH CH OH, and finally CH2 OH. So these are the products that you can expect to observe in this reaction, and make sure the reaction is balanced as well. So you can see over here on both sides the reaction is balanced. If you take a look at other answers, you will observe on both sides the reaction is completely balanced. Now let's move on to the next part. What is the name of the reaction observed here? We have seen this earlier as well. This reaction is a trans-esterification. Trans-esterification reaction. This is a trans-esterification reaction. Let's move on to the next part. The vegetable oil above is a unsaturated vegetable oil that contains carbon-carbon double bonds. State the number of carbon-carbon double bonds present in one molecule of X. So in the theory part, students, we explain this part a little bit. So we will go over that one more time. So the terminal carbons usually have 3 hydrogens, and the carbons that are found in the middle of a hydrocarbon chain usually has only 2 hydrogens if the hydrocarbon chain is a saturated hydrocarbon. Right. So now you can see, if you try to write its formula, now there are altogether 5 carbons. So since each carbon has at least 2 hydrogens, except for, actually each carbon has 2 hydrogens precisely, except for the terminal carbon. Terminal carbon has an additional hydrogen. But we will, for the time being, disregard this additional hydrogen here that the terminal carbon has and consider all the carbons are equal, having 2 hydrogens. So if that is the case, how many hydrogens should be there? If each carbon have 2 hydrogens, how many hydrogens should 5 carbons have? It will be 2 multiplied by 5. That means 10. And apart from that, there's going to be 1 terminal carbon. So that will bring 1 more hydrogen. So at that point, students, for this section of the hydrocarbon, the formula will be C5H11 for this section of the hydrocarbon. However, for the given hydrocarbon over here, we can see the formula is C21H39. C21H39. We'll write it down somewhere. So C21H39 was the formula of the hydrocarbon section of this fatty acid. So if there are 21 carbons and if the hydrocarbon section here is saturated, how many hydrogens can we expect? We can expect, if you directly write the number of hydrogens here, in a saturated hydrocarbon with 21 carbon atoms, we can expect 21 multiplied by 2 plus 1 many hydrogen atoms. So basically that is 42 plus 1 is 43. We can expect 43 hydrogen atoms. So how many hydrogen atoms are missing here? In this particular formula, we have, we can write hydrogen atoms that are missing compared to a saturated hydrocarbon chain with 21 carbon atoms. So that is going to be 43 minus 39. So when I say over here hydrogen atoms that are missing, right, I'm referring to compared to a saturated hydrocarbon containing 21 carbon atoms, how many hydrogen atoms are missing in this unsaturated hydrocarbon? So we can see we are missing altogether 4 hydrogen atoms. Now students, we do know when we convert, now for an example over here, when we convert a hydrocarbon section like this, into a hydrocarbon section with a double bond, we can very clearly observe this difference. If you say we are comparing this to a hydrocarbon section with a double bond like so, we can very clearly observe that with the presence of the double bond, we have two hydrogens missing across the double bond. Across the double bond, from each carbon, one hydrogen is missing, so therefore altogether two hydrogens are missing. Over here, when there are no double bonds, each carbon held two hydrogens, but over here across the double bond, each carbon only holds one hydrogen. So now students, you can see over here when the double bond was introduced, we have lost two hydrogen atoms. We have lost two hydrogen atoms. So when there are four hydrogen atoms missing, that would indicate the presence of two carbon-carbon double bonds. So therefore we can say in this section over here, C21 H39 part of the hydrocarbon, we can say this is unsaturated true, and we can say there are two carbon-carbon double bonds. There are two carbon-carbon double bonds. So that is something you can work out the way we did here. Then they ask, state the number of carbon-carbon double bonds that is present in one molecule of X. So one molecule of X contains three of these groups. You can very clearly see here, if you take a look at the structure of X, C21 H39, I will repeat it three times here, 21 H39 and C21 H39. And this is connected to COO CH2. Again here also COO CH. COO CH2. So students, you can see in one molecule of X, we have three of these hydrocarbon parts, and in one hydrocarbon section like this, there were two carbon-carbon double bonds. So altogether, there will be 2 multiplied by 3, which is 6 carbon-carbon double bonds present here. 6 carbon-carbon double bonds presence can be observed in one molecule of X. So we can say in one X molecule, there are 6 carbon-carbon double bonds. There are 6 carbon-carbon double bonds. So that is the answer to this question. In the food industry, X vegetable oil is transformed into a spreadable solid fat. State the chemistry behind this process. So students, when it comes to unsaturated fatty acids, unsaturations actually create fatty acid chains that are not very stackable. When there are unsaturations, due to the unsaturation present, the fatty acid chain is not going to pack really well. However, if you are talking about saturated fatty acids, now you can see this is one unsaturated fatty acid. When another unsaturated fatty acid comes close to it, in order to pack really well, forming intermolecular forces between the two molecules, it is not going to be that easy, and the strength of the intermolecular forces will be weak. So therefore, they will not pack really well, and the intermolecular forces of attraction between these molecules will be very small, resulting in them turning into liquid fats, or we can say these stay as oils, liquid oils. However, if you are referring to saturated fatty acids have this structure, and saturated fatty acids can easily pack really well, and the intermolecular forces, the strength of the intermolecular forces that are seen are going to be somewhat higher compared to the intermolecular forces and their strength observed in unsaturated fatty acids. Saturated fatty acids have stronger intermolecular forces of attractions between them. So due to this packing and the type of intermolecular forces or the strength of the intermolecular forces that are seen, you will observe that saturated fats majority of the time are present as solids at room temperature. So if you can convert these unsaturations here, or in other words double bonds, into single bonds, or if you convert these unsaturated fatty acid chains into saturated fatty acids, at that point you will be getting a solid fat at room temperature instead of a liquid oil. So we can convert a carbon-carbon double bond, as you may know, into a carbon-carbon single bond through a process known as hydrogenation. We can add hydrogen in the presence of a catalyst like nickel. We can break the double bond and introduce hydrogen atoms across the double bond. So this is, now over here there were hydrogens, right? So I have only indicated a section of a hydrocarbon chain. You can see there was a double bond here, but we can add hydrogen across the double bond by carrying out this hydrogenation reaction. So students, when we carry out the hydrogenation process, we will have these unsaturations turned into a single bond, meaning the resultant product is a saturated fatty acid, or in the triglyceride, the saturated fatty acids, they pack really well, causing it to turn into a solid fat instead of it remaining as a liquid oil. So that is what is happening in the production of margarine. We have vegetable oils that are hydrogenated because vegetable oils have unsaturated fatty acids in the triglyceride. So in the triglyceride, the unsaturated fatty acid chain, since it is not going to have this linear arrangement that we see over here, since they have this bent shape compared to saturated fatty acids, they don't pack really well. So therefore, when we carry out the hydrogenation process, the hydrocarbon section that has these unsaturations will be saturated later on, which will allow them to pack really well and turn into a solid fat. So vegetable oils can be turned into margarine or a solid fat through hydrogenation process, right? So vegetable oils, just to give you an idea, since we keep referring to them as the fatty acid chains, let's get a bit of a clearer idea. So we have CH2, CH, now this is a triglyceride that I'm trying to draw. So over here, students, what we have is a fatty acid that is bonded to the OH group of the glycerol. So here, this whole section came from a fatty acid. That's why we keep calling this R group the fatty acids hydrocarbon group. However, this entire molecule is going to be a triglyceride. This is a triglyceride, but we were referring to the R group here, right? We were referring to the R group. Since the R group came from a fatty acid, so we more commonly refer to this section as a fatty acid section of a triglyceride. And fatty acid section of a triglyceride contains the hydrocarbon group, and over here what we referred to was the hydrocarbon section of the fatty acid that is seen in the triglyceride. So yes, when these hydrocarbon sections, when they don't pack really well, we have the oils produced, but when they pack really well, we produce the solid fat. So that is why when we carry out this hydrogenation process, we can convert vegetable oils into a margarine or a solid fat. Right, let's move on to the next part. Formula of the diesel fuel obtained through crude oil is given here. Write the balanced chemical equation for the complete combustion of this molecule. Right. So we know complete combustion means we will form carbon dioxide and water. Complete combustion results in forming carbon dioxide and water. So there are 16 carbons, so I can expect 16 carbon dioxide molecules here. There are 34 hydrogens. So since hydrogens are coming in twos here, we will have to get over here 17 water molecules. 17 multiplied by 2 is 34. And then we have to account for the oxygens. So you can see over here we have 16 into 2, 32 oxygens, and 32 oxygens plus 17. 32 plus 17 is going to be 49. Can we just write 49 in front of oxygen here? No, as we can see, oxygen comes as 2 oxygen atoms, or in other words, an oxygen molecule is present here. So therefore, to get to the correct number of oxygens, you'll have to divide it by 2. So now the equation is balanced. We have 49 divided by 2 oxygen molecules, meaning we have overall 49 oxygen atoms. 16 into 2 is 32. 32 plus 17 oxygen atoms. 32 plus 7 is 39. 39 plus 10 is 49. So therefore, the number of oxygen atoms are balanced. But do we keep the equation this way, in this form? No, we will erase, or we will multiply all of these terms by 2. We can erase this and do the multiplication and write, but just for clarity, I will show that each of these is multiplied by 2, and in doing so, you will see 49 divided by 2 just turns into 49. Everything else also gets multiplied by 2. So this becomes 2C16H34. This becomes 49O2. This becomes 32CO2. And this becomes 34H2O. So 34 into 2 is altogether 68 hydrogens. Do we see 68 hydrogens? Yes, 34 into 2 is present here as well. And then 32 carbons are present here. We can see 32 carbons here as well. We can see 32 into 2 is 64 oxygens. 64 oxygens plus 34 oxygens is going to be 98 oxygens. 49 multiplied by 2 is 98 oxygen. So this equation is now completely balanced. So with that, students, we conclude our question discussion that is revolving around the preparation of biodiesel. So students, in the beginning, we went through all of the theory parts that revolve around biodiesel, not only biodiesel, but also bioethanol as well. And then we went into the lab and actually a prepared biodiesel. And here we discussed a very important few questions that are revolving around biodiesel. So with that, students, we hope you have now built up a good enough understanding of biodiesel and its manufacturing process. So we will conclude this experiment 43, preparation of biodiesel, and we will see you again in the next experiment.